Ben and Jerry's, Dunkin' Donuts, and Lay's Crisps do not become iconic by accident. A pint has to stay creamy while carrying chunks. A donut has to glaze at exactly the right moment, and a crisp has to be sliced so thin it almost disappears before it snaps. In this video, we uncover the hidden factory process that turns cream dough and potatoes into three foods people keep coming back to. Ben and Jerry's ice cream mix enters the freezer barrel as a smooth liquid, then leaves as a thick, semi-frozen stream ready to catch chunks, swirls, and ribbons. The liquid mix is cold before it reaches the freezer. It has already been blended, pasteurized, homogenized, aged, and balanced for fat, sugar, milk solids, and stabilizers. At this point, it looks like heavy cream with dissolved sweetness and flavor. Inside the freezer barrel, rotating scraper blades drag across a chilled metal wall. A thin film of ice cream freezes against that wall almost instantly. The blades scrape it away before it becomes a solid sheet. The scraped crystals mix back into the liquid. More liquid touches the cold surface. More crystals form. The cycle repeats rapidly, building a creamy frozen structure instead of a hard block of ice. Air is added at the same time in controlled amounts. The air is broken into tiny bubbles and distributed through the mix. The liquid thickens as it transforms into soft ice cream. The freezer does not finish the product completely. It produces ice cream that is cold, dense, and pumpable. It must still be soft enough to accept cookie dough, brownies, chocolate pieces, nuts, caramel, fudge, fruit preparations, or other inclusions without breaking the machinery or crushing the pieces. Before this freezing step, the dairy base is built in stainless steel tanks. Cream, milk, skim milk solids, sugar, liquid sweeteners, stabilizers, and emulsifying ingredients are measured into the batch system. The ingredients enter by weight or flow rate. The tank agitator keeps the mixture moving so powders hydrate and liquids disperse. The dairy fat is one of the main structural elements. It gives richness and helps the frozen mix hold air. Sugar lowers the freezing point, so the final ice cream does not become rock hard at freezer temperatures. Milk solids add body. Stabilizers help control ice crystal growth and improve texture after hardening. Dry ingredients are added carefully. Sugar flows easily, but stabilizers can clump if they hit the liquid too quickly. A powder induction system pulls dry materials into a fast-moving stream of liquid, dispersing them before they form lumps. The tank gradually becomes uniform. Flavor bases may be added to the liquid mix at this stage. Vanilla, chocolate, coffee, fruit bases, or other liquid ingredients can be blended into the dairy stream. Cocoa ingredients require strong mixing because cocoa powder resists wetting and can form dark clumps if not dispersed properly. Chocolate mixes become darker and thicker as the cocoa hydrates. The blended mix is pumped through filters to remove undissolved particles before heat treatment. It then moves through a pasteurization system. In a continuous plate heat exchanger, the mix flows between thin stainless steel plates while hot water or steam-heated fluid moves on the other side. Heat transfers quickly through the metal, raising the mix temperature under controlled conditions. The hot mix passes through a holding tube for the required time. The flow rate and tube length control the exposure. After holding, the mix enters the cooling side of the exchanger, but first, it may pass through a homogenizer. Homogenization forces the hot mix through very small gaps under high pressure. The fat droplets are broken into smaller droplets and spread evenly through the liquid. This creates a smoother mix and improves body. Without this stage, fat could separate or create uneven texture in the finished ice cream. After homogenization, the mix is cooled quickly. Cold fluid on the opposite side of the heat exchanger pulls heat away. The mix exits cold and moves into aging tanks. These tanks hold it at low temperature for several hours. Slow agitators keep the mix uniform without whipping in air. During aging, fat crystallizes into a stable form. Stabilizers fully hydrate. The liquid becomes slightly thicker. This step prepares the mix for freezing. Aged mix whips better, freezes more smoothly, and carries inclusions more evenly. Inclusion preparation happens separately from the dairy mix. Cookie dough pieces are formed from dough, cut into small chunks and chilled or frozen so they remain distinct inside the ice cream. Brownies are baked in sheets, cooled, cut into cubes, and frozen or chilled to hold their shape. Chocolate chunks are formed, cooled, broken, or cut to size and screened so only the correct pieces continue. Nuts are roasted or prepared, cooled, and sized. Caramel cups, fudge flakes, candy pieces, or baked inclusions are held cold so they do not smear when added. Each inclusion must be strong enough to pass through the feeder, but tender enough to bite through in the final product. Swirls are prepared in heated or chilled holding systems depending on the ingredient. Fudge swirl is cooked into a thick, glossy sauce. Caramel is blended and held at a temperature where it flows but does not become watery. Fruit swirl contains fruit preparation, sugar, and stabilizing ingredients to keep the texture spoonable at frozen temperatures. These swirls do not enter the main mix tank. They are added after freezing, so they remain visible as ribbons rather than disappearing into the base. The timing is important. If a swirl enters too early, it blends into the ice cream and becomes a uniform color. If it enters too late, it may not distribute across the pint. The semi-frozen ice cream exits the continuous freezer and enters a fruit feeder or ingredient feeder. This machine meters solid inclusions into the moving ice cream stream. A hopper holds the chunks. An auger or pocketed rotor releases them at a controlled rate. The pieces fall into the ice cream and are folded through by the flow of the product. The feeder must avoid crushing the inclusions. Cookie dough chunks, brownie cubes, and chocolate pieces pass through wide openings and gentle mixing zones. The goal is not to grind them into crumbs. The goal is to suspend large, recognizable pieces throughout the dense, frozen base. The stream then moves toward the variegate or swirl injector. Thick sauce is pumped through dedicated lines and injected into the ice cream as it moves toward filling. The sauce enters in ribbons, streaks, or bands. It does not fully mix. It travels as separate colored paths inside the base. The product now contains frozen ice cream, air cells, ice crystals, fat structure, chunks, and swirl. It is soft enough to pump, but thick enough that pieces do not immediately sink. It reaches the pint filler through short, insulated piping. Empty Ben & Jerry's pint containers feed into the filling line. The paperboard tubs are stacked and separated one at a time. Each container is placed into a pocket or held beneath a filling nozzle. The filler must handle a product that is partly frozen and full of pieces. The nozzle deposits ice cream into the pint in a controlled pattern. It may fill from the bottom upward or use a rotating motion to distribute swirls and chunks. The product enters as a thick rope, folding into the container and building upward. Large inclusions settle into the base as the pint fills. The fill level is controlled by volume or weight. Too little product creates an underfilled pint. Too much product can interfere with lidding or create product on the rim. The filler cuts off cleanly so the rim remains clear. Some flavors need extra topping or a core style addition. In those formats, the filler may deposit part of the ice cream, inject a central stream of caramel, fudge, cookie butter, or another component, then finish with more ice cream. The core must remain centered and thick enough to stay visible when scooped. After filling, a lid is placed on the pint. Lids feed from a magazine or hopper, separate one at a time, and press onto the rim. The container now holds soft ice cream that is shaped but not yet fully hardened. The pints pass through check weighing. The machine weighs each container and rejects any pint outside tolerance. Vision systems inspect lid placement, container condition, print orientation, and visible rim contamination. The filled pints move quickly toward hardening. This is where the soft, frozen product becomes stable enough for storage and distribution. The pints enter a hardening tunnel or spiral freezer. Very cold air moves at high speed around the containers. Heat leaves the pint from the outside inward. The ice cream firms against the container wall first. The center hardens more slowly. The air movement must be strong because pints are thick packages, and the product contains chunks and swirls that affect how heat transfers. Dunkin' Donuts dough rings swell inside a humid proofing chamber before they ever touch hot oil. The rings enter the chamber, pale, flat, and soft. They ride on trays or open belts in steady rows. Warm air surrounds them from all sides. Moisture in the chamber keeps the surface flexible, while yeast activity expands the structure from within. The dough slowly rises, rounding at the edges and lifting away from its original cut shape. The proofing stage controls the lightness of the finished donut. The dough must inflate enough to float in the fryer, but not so much that it weakens and collapses. Temperature, humidity, and travel time are balanced, so every ring leaves with a soft skin, open internal cells, and enough strength to survive transfer. Before reaching this chamber, the rings are cut from a sheet of dough. The sheet moves beneath a rotary cutter fitted with circular blades. One blade cuts the outside edge of the donut. A smaller blade cuts the center hole. Each rotation presses through the sheet and releases another row of rings. The cutter must work cleanly. If the dough sticks, the ring stretches. If the blade is dull, the edge tears. A clean cut gives the donut a smooth outline, a centered hole, and a predictable expansion path during proofing. The surrounding dough web lifts away after cutting. It separates from the rings and moves onto a return belt. This recovered dough can be added back in controlled amounts, so the sheeting process remains efficient without overworking the next batch. The dough sheet itself is formed by rollers. Mixed dough enters the sheeting line as a thick, elastic mass. The first roller pair compresses it into a slab. Later rollers reduce the thickness step by step. The dough becomes broader, flatter, and more even with every pass. Side guides keep the sheet aligned. Scrapers remove dough from the roller surfaces. A light flour dusting system prevents sticking without covering the dough in excess powder. The final sheet thickness determines the weight and height of the raw donut. The dough starts in a mixer. Flour enters after sifting, which breaks up compacted lumps and removes oversized particles. Sugar, yeast, salt, milk solids, and leavening ingredients are dosed separately. Water flows in at a controlled temperature. Fat, egg ingredients, and flavor components enter through measured lines. The mixer begins at low speed. Flour absorbs water and turns from dry powder into damp clumps. The mass gathers around the mixing arms. As mixing continues, the dough stretches and folds repeatedly. It becomes smoother, warmer, and more elastic. The dough must be strong enough to trap gas in the proofer, but soft enough to fry into a tender crumb. Mixing time, hydration, fat level, and final temperature all shape this structure. When the dough reaches the target texture, it leaves the mixer and moves toward dividing. Dividing cuts the large dough mass into workable portions. These portions rest briefly before sheeting. Resting lets the dough relax, which helps it roll smoothly without shrinking back. The relaxed portions feed into the rollers and become the continuous sheet used for cutting. After proofing, the swollen rings move toward the fryer. Transfer equipment places them gently onto the oil surface. The dough is fragile at this point because it contains many gas cells. A rough drop would flatten the donut or distort the ring. The fryer carries the donuts in lanes through hot oil. As each ring touches the oil, steam forms at the surface. the lower side, sets first. Bubbles race along the outer edge and through the center hole. The donut expands slightly as heat moves inward. A turning device flips the donut halfway through frying. The second side enters the oil and browns to match the first. The surface turns golden while the inside remains soft and airy. Oil temperature stays within a narrow range so the donut cooks through without becoming greasy or overdark. Loose crumbs are removed from the oil by filtration. This keeps dark fragments from sticking to later donuts. The fryer belt continues moving at a fixed speed, giving each donut the same exposure time. The fried donuts leave the oil on a draining conveyor. Excess oil falls through the mesh. The donuts remain hot, soft, and slightly fragile. Their crust is set, but the interior is still tender. From here, different varieties, split into separate finishing paths. Glazed donuts move forward while still warm. The glaze system uses a heated tank filled with sugar, water, and flavoring ingredients. Agitators keep the glaze smooth. A pump lifts it to an overhead trough where it falls as a continuous curtain. The warm donuts pass under the curtain. Glaze coats the top, slides down the sides, and flows around the inner ring. Extra glaze drains through the open conveyor and returns to the tank. The coating is thin at first and glossy, like a wet shell. The glazed donuts continue through a setting zone. Air moves over the surface. Moisture leaves the glaze. The coating tightens and becomes a smooth sugar layer that clings to the golden donut below. Chocolate frosted donuts follow a cooler path. They leave the fryer and cool longer before icing. If the donut is too hot, the chocolate coating becomes thin and runs. At the right temperature, the top surface receives a measured layer of icing. The donut passes beneath a coating head or touches a controlled icing surface. Chocolate icing spreads across the top and stops before fully covering the underside. The coating forms a smooth cap. It stays soft briefly, which allows toppings to attach. Sprinkle donuts move directly beneath a topping dispenser. Small colored pieces fall in a controlled shower. They strike the tacky icing and remain embedded. Loose sprinkles fall between the donuts and are collected away from the product path. Filled donuts begin as solid rounds, not rings. The cutter makes circular dough pieces without a center hole. These rounds proof into soft pillows and fry on both sides. After frying, they cool enough to receive filling without melting or leaking. The filling station uses narrow injection nozzles. Each nozzle enters the side of a donut. A pump delivers a measured amount of cream, jelly, custard, or flavored filling into the center. The filling spreads inside the soft crumb and slightly expands the donut. The nozzle withdraws, leaving a small entry mark. The filled donut may then be glazed, powdered, iced, or striped. Powdered donuts pass through a dusting chamber where fine sugar falls over the surface. The donut turns or moves through the powder stream, picking up an even coating. Excess powder drops through screens. Striped donuts pass beneath small decorating nozzles. Thin lines of icing cross the top while the donut moves on the belt. The nozzles release a steady flow, and the belt speed controls the spacing and length of the stripes. Cake donuts use a different batter system. Instead of yeast dough, a thicker batter is mixed with flour, sugar, fat, liquid ingredients, and chemical leavening. The batter is deposited directly into hot oil through a shaped depositor. As it fries, the batter expands and sets into a denser ring with a different crumb. The cake donut depositor controls the shape by extruding batter in a ring. The batter drops into the oil, floats, and fries. The outside becomes lightly crisp, while the inside sets into a moist cake texture. These donuts can be glazed, sugared, frosted, or coated after cooling. Donut holes can come from center cuts or separate depositing equipment. They fry as small, round pieces. Because they are smaller, they cook quickly and move through coating or glazing systems in large quantities. They may be tumbled in glaze, sugar, or powdered coatings before packing. After finishing, all donut varieties move through inspection. Cameras check color, shape, topping coverage, glaze thickness, icing placement, missing sprinkles, broken edges, and distorted centers. Filled donuts can be checked by weight to confirm the correct amount of filling. Defective pieces are rejected automatically. Accepted donuts are spaced by timing belts. The belts create separation so toppings do not smear. Guide rails organize the flow into lanes for packing. Different varieties may be routed into separate packing areas or assembled into assortments. Lay's crisps leave the fryer as thin golden slices, still shimmering with hot oil before seasoning turns them into finished chips. The slices ride up an inclined conveyor with open gaps beneath them. Oil drains away as the chips move forward. They are fragile at this point. Their surfaces are crisp, blistered, and lightly curled from the sudden loss of moisture inside the fryer. Air moves across the belt to cool them just enough for seasoning to cling correctly. The fryer is the center of the transformation. Raw potato slices enter pale, wet, and flexible. A few seconds later, they are crisp, rigid, and golden. Hot oil surrounds each slice. Water inside the potato flashes into steam and escapes as bubbling. The slice becomes thinner as moisture leaves. Starch gelatinizes first, then dries into a brittle structure. Oil temperature is controlled across the fryer. If the oil is too cool, the slices absorb too much oil and turn heavy. If it is too hot, the outside darkens before the center dries. The conveyor speed controls how long each slice remains in the oil. The result must be a crisp chip with a light golden color and clean break. Loose fragments and small potato solids fall away during frying. A filtration system continuously removes these particles from the oil. This prevents dark specks from burning and sticking to later chips. Fresh oil is added in controlled amounts to maintain the frying system. Before the fryer, the potatoes are sliced with high-speed cutting heads. Whole peeled potatoes enter a rotating slicer. Sharp blades shave them into very thin sheets. The slice thickness is tightly controlled because even a small change affects texture, cook time, color, and crunch. The cutting action is fast and clean. Each potato spins or passes against the blades, producing a stream of round or oval slices. The slices fall into a water flume immediately after cutting. Water separates them from each other and carries away free starch from the cut surfaces. Surface starch must be reduced before frying. Too much starch can make slices stick together or darken unevenly. The slices pass through washers where moving water lifts starch from the surface. The water becomes cloudy as starch leaves the potato. After washing, the slices move through dewatering equipment. Shaker conveyors and air knives remove surface water. If wet slices enter the fryer, oil turbulence increases and frying becomes less controlled. The slice must still be raw and moist inside, but the outside cannot carry excess water. The potatoes reach the slicer after a long preparation route. Whole potatoes arrive at the factory in bulk. They are unloaded into receiving hoppers and carried by conveyors toward cleaning equipment. Dirt, stones, vines, and field debris must be removed before the potatoes reach the process line. A dry separation stage removes loose soil and heavy objects. Rollers, screens, and conveyors shake the potatoes while smaller debris falls away. Stones can be separated by density systems because they behave differently from potatoes in water or mechanical sorting. The potatoes then enter washing drums. Water sprays across them while rotating drums tumble the load. The skins rub against each other and against the drum surface. Soil loosens and drains away with the wash water. The potatoes leave cleaner, smoother, and ready for inspection. Sizing equipment separates potatoes by diameter. Very small potatoes do not slice into the right chip size. Oversized potatoes may be diverted or trimmed. Uniform sizing helps the slicer produce consistent chips and helps the fryer cook them evenly. Some potatoes move through peeling equipment. Steam peeling uses high-pressure steam to loosen the skins quickly. When pressure drops, the skin separates from the flesh. Brushes or rollers remove the loosened skin. Other lines use abrasive peeling, where rough surfaces rub the skin away. After peeling, the potatoes pass through inspection and trimming systems. Optical sorters examine the surface for dark spots, green areas, bruises, or defects. Jets of air or mechanical diverters remove potatoes that do not meet the programmed limits. The accepted potatoes continue towards slicing. Potato variety and solids level matter for crisp production. A good chip potato has enough dry matter to fry into a crisp slice without becoming leathery. Potatoes with too much sugar can brown too quickly. Potatoes with too much water require longer frying and may produce weak texture. Once the raw slices are washed, dewatered, and fried, they enter the seasoning system. The chips leave the fryer and pass through a cooling zone before entering a rotating seasoning drum. The drum is tilted slightly and turns continuously. Chips enter at one end and tumble gently toward the other. The rotation exposes different surfaces without crushing the chips. Seasoning is applied as a fine powder through controlled feeders. For classic salted Lay's, salt. Crystals are metered onto the chips while they are still warm and lightly oily. The oil film helps the salt stick. For flavored varieties, powders contain salt, spices, dairy powders, onion, garlic, cheese flavors, barbecue seasoning, sour cream flavor, vinegar components, or other dry ingredients. The seasoning feeder must deliver a steady flow. If too much powder drops at once, some chips become overloaded while others remain plain. If too little is applied, the flavor becomes weak. The drum angle, rotation speed, chip flow rate, and powder rate work together. Inside the drum, chips slide, lift, fall, and rotate. The seasoning dust spreads across curves, blisters, and edges. The sound changes from the sharp crackle of dry chips to a softer rattling as powder coats the surfaces. The chips exit evenly seasoned and ready for inspection. Broken chips and tiny fragments are separated before packaging. Vibrating conveyors can remove fines through small openings. Optical systems inspect color and detect dark chips or burnt pieces. Metal detectors scan the product stream. Defective material is diverted automatically. The accepted chips move to weighing. Because chips are light and irregular, they cannot be filled by simple volume. A multi-head weigher is used. Chips feed into multiple small weighing buckets positioned around the machine. Each bucket holds a small portion. The control system calculates which combination of buckets adds up to the target bag weight. Those buckets open together, dropping the exact portion into a funnel. The chips fall quickly, but must not be crushed. Smooth surfaces and controlled drop heights protect the fragile pieces. Packaging film unwinds below the weighing system. The film is printed on the outside and has barrier layers that help protect crispness. It moves over a forming collar, which shapes it into a vertical tube. The edges of the film meet at the back. A vertical sealing jaw closes the back seam. The bottom seal is made first by horizontal jaws. Then the weighed chips drop into the open tube. The jaws close again above the product, sealing the top of one bag and the bottom of the next. Before final sealing, nitrogen gas may flush the package. The gas reduces oxygen and creates a cushion inside the bag. The pillow shape protects chips from crushing and helps preserve crisp texture. The bag is not filled tightly with chips. It contains product and protective headspace. The horizontal jaws cut between seals, releasing one finished bag. The next bag is already forming above it. This process repeats rapidly, turning a continuous roll of film and timed chip portions into sealed Lay's bags. Cadbury Dairy Milk is manufactured by transforming milk and sugar and cocoa into a low-moisture chocolate crumb or chocolate mass, refining it into a smooth suspension, conching it to stabilize flow, tempering it to lock stable cocoa butter crystals, then molding and packing while temperature and viscosity stay tightly controlled. Milk handling is treated as a structural step rather than a flavor step because dairy solids determine body and sweetness balance. Milk can enter as liquid milk, concentrated milk, or milk powder depending on plant design. Liquid streams are filtered and held at controlled temperature for predictable pumping. Powder streams are sieved to remove clods because clods do not hydrate evenly and later create texture specks. Sugar is screened to control crystal size and to remove lumps that would resist refining. Cocoa components are prepared as cocoa liquor and cocoa butter streams held warm so they remain pumpable. Cocoa powder streams are sifted when used to remove compaction lumps. All dry ingredients are kept low in moisture because water in chocolate causes thickening and unstable flow. A key feature of many milk chocolate lines in this style is crumb production, which converts milk and sugar into a dry solid that carries developed dairy notes and improves process stability. Crumb production starts by combining milk and sugar in a cooker. The mixture is heated while being mixed, so sugar dissolves and water begins to evaporate. Heating is controlled to drive off water without scorching milk solids. As water leaves, the mixture becomes thicker and begins to form granular solids. The cook continues until the mass becomes a dry or semi-dry crumb with low residual moisture. During crumb cooking, thermal history is tightly managed because it controls flavor development and functional behavior. Too gentle a cook leaves high moisture and produces crumb that later thickens the chocolate unpredictably. Too aggressive a cook darkens sugars and drives strong cooked notes that can overwhelm the profile. The endpoint is set by moisture content, and by the way, the crumb fractures when broken. When the endpoint is reached, the crumb is cooled and milled into a manageable size so it can be blended uniformly later. Cocoa liquor and cocoa butter are prepared in parallel. Cocoa liquor is held warm so it stays fluid and is filtered to remove solid lumps. Cocoa butter is melted in jacketed tanks and filtered for clean metering. These fat streams define the continuous phase of the final chocolate, and they also control viscosity through the downstream steps. Mixing combines crumb with cocoa liquor, cocoa butter, and additional sugar or milk solids as required by the recipe. The goal is to create a homogeneous pre-mass where solids are evenly distributed in fat. Mixing is done in high-torque mixers with wall scraping because the mass can be thick before refining. The mixture transitions into a paste with consistent color and no dry pockets. At this stage, the mass is not yet smooth. Sugar crystals and crumb particles are still large enough to be detected on the tongue. Refining is performed to reduce particle size. The pre-mass is fed to roll refiners or other milling systems. In roll refining, the mass passes through a series of rolls with decreasing gaps. Each pass squeezes and shears particles smaller. The refined output leaves the last roll as a thin film that breaks into flakes. These flakes have high surface area and must be processed into conching quickly to prevent moisture pickup. Conching is the step that transforms refined flakes into a smooth flowing chocolate with stable flavor. The flakes enter a conche where mechanical work coats each particle with fat and breaks down remaining agglomerates. Heat keeps cocoa butter fluid and supports moisture removal. Airflow through the conche carries away moisture and volatile compounds. Moisture removal is essential because even small amounts of water cause chocolate to seize and become thick. Conching also stabilizes rheology by reducing friction between particles. Early in conching, the mass can be dry and pasty. As fat distribution improves, the mass becomes smoother and viscosity drops. The concha profile is tuned to reach a target viscosity for molding and enrobing while maintaining the desired flavor. Over-conching can reduce throughput and strip some volatile character. Under-conching leaves high viscosity and inconsistent snap. Emulsifiers are typically added near the end of conching. Lecithin improves particle wetting and reduces yield stress. Another flow modifier can be used to reduce viscosity further at a given fat level. These additives are dosed precisely because small changes alter how chocolate behaves in deposit heads and tempering machines. The chocolate is then filtered and transferred to holding tanks with gentle agitation to keep the suspension uniform. Tempering is the controlled crystallization of cocoa butter that gives dairy milk its stable set and gloss. Chocolate is first heated to melt existing crystals fully. It is then cooled under agitation so new crystals form. It is then reheated slightly to melt unstable forms while keeping stable seed crystals. The output chocolate contains a controlled population of stable crystals and remains fluid at the working temperature. Temper is monitored continuously because it drives mold release and surface quality. If temper is too low, the chocolate sets slowly and releases poorly and can bloom later. If temper is too high, viscosity rises and the chocolate becomes thick, causing poor mold, fill and thick edges. Tempering machines adjust cooling and heating in small increments to maintain the target crystal content. Molding shapes the chocolate into bars and blocks. Polycarbonate molds are cleaned and pre-warmed to prevent condensation. Depositors meter chocolate into each cavity with tight mass control. The filled molds pass over vibrating tables. Vibration removes trapped air bubbles and levels the surface. It also improves detail in any embossed features. Cooling tunnels set the molded chocolate. Cooling is staged to set the surface quickly without creating internal stress. The chocolate contracts slightly as it cools, which helps demolding. If cooling is too fast, the chocolate can crack or warp. If too slow, the line speed drops and molds remain occupied. Cooling also must avoid condensation because moisture on the surface can cause sugar bloom. After cooling, the molds are inverted and the bars release. Release depends on correct temper and correct cooling because the bar must contract away from the mold wall. Bars transfer to conveyors where they are inspected for surface defects. Weight checks confirm deposit accuracy. Bars with defects are diverted for rework. Rework is remelted and returned upstream in controlled ratios so it does not destabilize tempering. If the product includes inclusions or filled formats, the molding stage expands. Inclusions, such as nuts, are screened and kept dry. They can be placed into molds before chocolate deposition or blended into chocolate with controlled suspension. Filled formats use sequential depositing. A shell is deposited and partially set. A filling is dosed and then sealed with a chocolate back layer. Cooling profiles are adjusted because fillings change heat transfer and can insulate. After demolding, bars move to wrapping. Wrapping protects chocolate from oxygen, moisture, and abrasion. Bars are indexed into wrapping machines that fold foil or film around each bar. Fold geometry is controlled so edges are crisp and seals are tight. If an inner foil and outer paper wrap are used, the foil provides the barrier and the paper provides stiffness and print. Heat sealing or crimping forms the closure, depending on wrap type. Coded information is applied during wrapping or immediately after. Vision systems check wrapper alignment and seal integrity. Check weighers verify pack weight. Wrapped bars are then collated into cartons if needed. Cartons are erected and filled with a defined count. Cartons are closed and glued. Finished units are case-packed and palletized. The process control backbone for dairy milk is moisture management and particle size management and crystal state management. Crumb production drives moisture down and creates a stable dairy sugar matrix. Refining drives particle size down for smoothness. Conching drives off remaining moisture and stabilizes flow by coating particles with fat. Tempering builds the correct crystal population for gloss and snap and clean mold release. Cooling locks the structure, and wrapping protects it from temperature swings and humidity. Three Musketeers is manufactured by producing a highly aerated chocolate-flavored nougat center, forming it into a continuous slab, cutting it into bars, enrobing those bars in tempered chocolate, then cooling and wrapping while density and coating thickness remain tightly controlled. The defining step is the aeration system, because the bar's texture depends on holding a large volume of fine bubbles inside a stable sugar and fat matrix. The process, therefore, starts by building two streams that can be combined without collapsing air cells. One stream is a cooked syrup with a precise solids level. The other stream is a foamed phase that carries air at a controlled density. Syrup preparation begins with sugar and glucose syrup metering. Granulated sugar is screened to remove clumps and to keep dissolution predictable. Glucose syrup is held in jacketed tanks so it pumps at stable viscosity. Water is filtered and tempered because inlet temperature affects dissolving rate and cooker stability. The streams enter a dissolver where agitation produces a clear solution. Strainers remove any undissolved grains because grains concede crystallization and create a gritty center. The clear syrup then enters a continuous cooker where heat drives off water. Many systems heat under pressure, so temperature can rise quickly without boiling in the coil. After the heating zone, the syrup may enter a flash stage where pressure drops and water vapor leaves rapidly. This trims moisture to the target. Moisture control here sets final nougat resilience. Too much moisture yields a soft center that can deform under cutters. Too little moisture yields a tough center that loses its light bite. While the syrup is being cooked, the aerated phase is prepared. A protein solution is mixed to a defined concentration and then sent to a continuous aerator. Airflow and rotor speed are controlled to create small bubbles and stable foam. Foam density is monitored continuously because it is the most direct indicator of final bar lightness. The foam must be stable enough to survive contact with hot syrup. It must also be fine enough to produce a smooth bite rather than large voids. The cooked syrup is cooled slightly to a controlled blending temperature and then combined with the foam in a continuous mixer. The mixer is designed to fold the streams together rather than whip. Folding distributes syrup through the foam while preserving the bubble structure. The syrup heat partially sets the protein films around bubbles and locks in the microcell network. Chocolate flavor is built into the nougat by adding cocoa components and sometimes chocolate liquor or cocoa powders at controlled points. These additions must be dispersed without deflating the foam. They can be introduced as fine powders, pre-blended with part of the syrup, or as a liquid chocolate. Stream introduced downstream of the highest shear zone. Fat is injected as a thin stream to soften texture and reduce stickiness. Emulsifiers can be added in small doses to improve stability and control viscosity. Once mixed, the aerated nougat exits as a warm plastic mass with controlled density and viscosity. It is deposited onto a moving belt as a continuous slab. A spreader head lays down the slab at a defined width. Gauge rollers and leveling bars set thickness. Thickness control is critical because it determines bar mass and also affects cooling time. The slab enters a cooling tunnel where temperature drops in stages. Staged cooling prevents a hard skin from forming over a warm interior because that skin can crack and create weak planes during cutting. As the slab cools, the bubble structure stabilizes further. Fat begins to crystallize, and the nougat transitions from plastic to firm yet compressible. The target firmness is set, so the slab can be cut cleanly without smearing. If the slab is too warm, knives drag and deform edges. If too cold, the slab can fracture at the surface and create rough edges that show through the chocolate coat. Edge trimming is often used to remove uneven slab edges. Trims are collected as controlled rework. Rework must be managed carefully because aerated material behaves differently than fresh mix. Excess rework can shift density and bubble size distribution. The main slab then moves into lane cutting. Rotary knives slice the slab into long ropes of constant width. A crosscutter then slices the ropes into bar lengths. Cutter timing is synchronized with belt speed, so each bar length is consistent. The cut centers are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges between bars. Transfer points are designed with low drops and soft transitions because aerated centers dent easily. Some lines include a brief pre-chill to firm the surface. Firmer surfaces accept chocolate more evenly and reduce deformation as the center passes through the curtain. Chocolate coating is prepared in a separate system where temper is the key variable. Chocolate is melted and filtered to remove unmelted particles. Tempering then creates stable seed crystals by controlled cooling and reheating. Working temperature is set so viscosity remains stable at the curtain. Viscosity controls the thickness of the coating and therefore the final chocolate to center ratio. Enrobing coats the bar with a top curtain and a bottoming system. Bars pass through a chocolate waterfall that coats the top and sides. The underside is coated by a roller or a bath section that lays a consistent base. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot at the base. Air knife settings are tuned to remove excess without exposing corners. Because the center is soft, air knife force is balanced so it does not deform the nougat under the coat. A pattern top can be applied by a stringer that drizzles thin chocolate lines over the wet surface. The drizzle must bond before the base coat fully sets. This requires a precise timing window between curtain exit and cooling tunnel entry. Pattern flow rate and nozzle spacing are synchronized with belt speed. Cooling tunnels set the chocolate. The first zone sets the surface quickly so the coating does not slump, and so the bar can be handled. Later zones cool more gradually to promote stable crystal growth and reduce bloom risk. Cooling must avoid condensation because moisture on chocolate creates sugar bloom and dullness. Tunnel humidity is controlled, and the bar exit temperature is set to support wrapping without scuffing. During cooling, the nougat center also equilibrates. The fat phase in the center continues crystallizing, and the bubble walls become more rigid. The center remains light and compressible, but it gains enough strength that handling pressure from wrappers does not deform it. The chocolate coat becomes a barrier that reduces moisture exchange and helps maintain texture over shelf life. Inspection follows cooling. Vision systems check for exposed edges and coating voids. Weight checks confirm bar mass and coating mass. Bars outside tolerance are diverted. Diverted product is handled as rework streams that are remelted for chocolate or reprocessed for nougat according to process rules. Wrapping begins once the bars reach a stable temperature. Bars feed into flow wrappers that form film around each unit and heat seal it. Seal temperature and dwell are controlled, so seals are tight without shrinking film onto the bar. Film tension is controlled to avoid scuffing the chocolate surface. Print registration aligns graphics to bar position. Coating adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Twix bars are manufactured by producing a crisp biscuit finger, applying a controlled caramel layer, enrobing the assembled sticks in tempered chocolate, then cooling and wrapping while moisture and viscosity remain tightly controlled. The process begins with the biscuit line because the biscuit defines the bar geometry and the snap that must survive caramel deposition and chocolate coating. Flour is sieved to remove lumps and to standardize flow. Sugar is screened so crystal size is consistent and does not tear dough during mixing. Fat is conditioned to a plastic state so it blends evenly and limits gluten development. Leavening salts are weighed precisely because they determine porosity and bite strength. Water and any dairy liquids are tempered because dough temperature controls how cleanly it sheets and cuts. Mixing is designed to create a short dough with limited gluten. Fat and sugar are first blended to distribute fat and reduce dry friction. If a creaming step is used, it is controlled to avoid excessive air because too much air weakens biscuit and increases breakage during handling. Dry ingredients are then introduced and mixed only until the dough becomes cohesive. Minimal mixing limits gluten formation and preserves a tender, crisp structure rather than a tough one. Dough conditioning follows. The dough rests so moisture equilibrates and the dough relaxes. Relaxation prevents snapback during sheeting. Dough temperature is held in a narrow range, so fat stays plastic. Warm dough smears on rollers. Cold dough cracks at edges and produces rough cutouts. Sheeting converts dough into a continuous band at a defined thickness. The dough passes through reduction rollers that gradually thin it. Gauge rollers set final thickness tightly because thickness drives bake time and final snap. Dusting flour can be applied sparingly to prevent sticking, but excess dust is avoided because it burns and creates specks. The sheet enters rotary cutting and docking. Rotary cutters punch long biscuit fingers. Docking pins create small holes through the dough. These holes vent steam during baking and prevent blistering and warping. The cut fingers transfer to an oven band. Scrap dough around the cutouts is lifted and recycled. Scrap ratio is controlled because repeated working increases gluten and changes dough behavior. Baking occurs in a tunnel oven with staged zones. Early zones set the shape as fat melts and moisture begins to leave. Leavening gases expand and create small pores. Mid-zones drive moisture down and develop a light golden color. Later zones finish drying so the biscuit reaches a low moisture endpoint. Moisture endpoint is critical because the biscuit must remain crisp under caramel and chocolate. If moisture remains too high, the biscuit will soften and lose snap. If moisture is too low, the biscuit becomes overly brittle and breaks during sandwiching and wrapping. After baking, the biscuit fingers exit the oven and enter cooling. Cooling stabilizes structure as fats resolidify. Cooling air is controlled and often dehumidified because dry biscuits can absorb moisture from humid air. The goal is a consistent exit temperature and moisture level. The cooled fingers are then aligned into lanes for caramel application. Caramel production runs in parallel because caramel must be depositable and stable. Sugar and glucose syrup are cooked with milk components to develop caramel flavor and reach an elastic solids endpoint. The cook drives off water until the caramel will hold shape at room temperature. Fat is added to smooth the caramel and reduce tack. The endpoint is set so the caramel bites cleanly without becoming glassy. Overcooked caramel becomes hard and can fracture when the bar is bitten. Undercooked caramel flows and smears in packaging. Caramel is cooled from cook temperature to a working temperature where viscosity is stable for deposition. It is held in jacketed tanks with gentle agitation to prevent skin formation. Pipes to the depositor are heated to prevent cold plugs. Viscosity is monitored indirectly by pressure and flow because a small temperature drift changes deposit weight and layer thickness. Caramel deposition applies a continuous layer onto the biscuit fingers. A slot depositor or multi-nozzle head lays caramel onto the moving biscuit lane. A leveling bar smooths the surface and sets thickness. Thickness must be uniform because it influences bite and chocolate coverage. If caramel is too thick, it can squeeze out under chocolate and create uneven edges. If too thin, the bar loses the intended caramel to biscuit balance. The biscuit temperature at deposition is controlled. Biscuit must be cool enough to remain crisp and to avoid melting caramel into the pores too deeply. It must not be so cold that caramel fails to bond. The line targets a temperature window where caramel adheres but does not soak. After deposition, the caramel-topped fingers pass through a cooling tunnel to set the caramel surface. Cooling must be staged so the surface firms without cracking. A firm surface is required before enrobing so caramel does not smear on belts. Once the caramel is set, the sticks are transferred to the enrobing line with controlled spacing. Spacing prevents chocolate bridges. Transfers minimize drop height because biscuit can crack and caramel can shear. The sticks may pass through a brief pre-chill to firm surfaces and improve chocolate flow behavior. Chocolate preparation is a separate stream where temper control is essential. Chocolate is melted and filtered. It is tempered to create stable cocoa butter seed crystals. Working temperature is set to maintain consistent viscosity. Viscosity determines how thick the chocolate curtain is and how much chocolate remains after air knife trimming. Enrobing coats the sticks in chocolate. A top curtain covers the caramel and sides. A bottoming system coats the underside so the biscuit is sealed. Excess chocolate drains through a wire belt. Air knives smooth the surface and control the foot thickness. Air knife settings must be tuned because too much air can expose corners, especially at biscuit edges. Too little air leaves thick feet that can crack during cooling. If a top pattern is required, it is applied immediately after the main curtain. A stringer deposits thin chocolate lines across the surface, while the base coat is still wet enough to bond. The stick then enters the cooling tunnel. Cooling sets the chocolate and locks the finished structure. The first zone sets the surface quickly to prevent slumping. Later zones cool gradually to promote stable crystal growth and reduce bloom risk. Cooling also reduces the internal temperature of caramel so it reaches its final elasticity. The exit temperature is set so the chocolate is hard enough for wrapping without scuffing. After cooling, the bars are inspected. Vision systems detect exposed biscuit corners and coating voids. Weight checks confirm portion control. Defective bars are rejected. Rework chocolate is remelted and returned upstream, while biscuit and caramel rework is handled separately because it carries moisture and texture changes. Wrapping begins with feeding bars into flow wrappers. Film is formed around each bar and sealed. Seal temperature and dwell are controlled so seals are strong without overheating the chocolate. Film tension is controlled to prevent scuffing. Print registration aligns graphics. Coding adds lot and date information. Wrapped bars are collated into multi-packs or cartons. Collation uses lanes and gating to group bars without impact. Cartons are erected and loaded and closed. Finished packs are case-packed and palletized. Hershey's milk chocolate is produced by taking dry solids that would feel gritty on the tongue, suspending them in cocoa butter and milk fat, then forcing that suspension through particle reduction, moisture stripping, and crystal control until it can be poured into molds and set into stable bars. Chocolate begins as a set of dry streams that must be kept dry. Sugar is received as granulated crystals and screened to remove clumps that resist grinding. Milk solids arrive as powders and are sieved because compacted lumps do not disperse evenly and later create specks. Cocoa solids arrive as cocoa liquor, cocoa butter, and sometimes cocoa powder, depending on the formula and plant layout. Cocoa butter is melted and filtered. Cocoa liquor is held warm, so it remains pumpable and is filtered to remove unmelted fragments. Water is kept out of all these streams because even small moisture content causes chocolate to thicken sharply. The first assembly step is a pre-mix that creates a uniform paste for refining. Melted cocoa butter and cocoa liquor create the continuous fat phase in a mixer. Sugar and milk powders are introduced gradually so they become wetted rather than forming dry islands. The mixer uses high torque and wall scraping because the mass is thick before refining. The goal is not smoothness yet, but even distribution of solids, so downstream mills see a consistent feed. Particle size reduction is then applied. Refining is performed with roll refiners or equivalent milling equipment that squeezes the paste through narrowing gaps. Each pass breaks sugar crystals and reduces the size of milk and cocoa particles. The target is a particle size below the tactile threshold on the tongue. When the chocolate reaches this range, its texture becomes smooth rather than sandy. The output of roll refining often emerges as thin flakes because the refined mass forms a film on the final roll and breaks off. Those flakes behave dry because they have huge surface area and not enough free fat coating at their surfaces. They also hold trace moisture and trapped air. If left untreated, they will make the chocolate thick and harsh. Conching is the step that fixes both flavor and flow. Conching combines heat, time, and mechanical work to coat particles fully with fat and drive off moisture. The refined flakes enter a conch where paddles knead the mass. Heat keeps cocoa butter fluid so it can spread across particle surfaces. Mechanical shear breaks down any remaining agglomerates and distributes fat uniformly. Airflow through the conch carries away moisture and volatile compounds. Moisture removal is critical because water causes particles to cling together and raises viscosity. During early conching, the chocolate may appear pasty and resistant. As conching continues, friction drops and the mass becomes more fluid and glossy. This change is the result of improved fat wetting and lower moisture. The conch is controlled to reach a defined viscosity and yield stress that matches the needs of molding equipment. Too thick, and the depositor will underfill corners and create air pockets. Too thin, and the bar edges will become heavy and the surface will be more prone to flow marks. Emulsifiers are typically added late in conching to fine-tune flow. Lecithin reduces yield stress by improving particle wetting. Additional emulsifiers can be used to further reduce viscosity at the same fat level. These additions are dosed precisely because small changes have large effects on how the chocolate runs through pumps, valves, and deposit heads. After conching, the chocolate is transferred to holding tanks with gentle agitation. Agitation prevents separation and keeps the suspension uniform. Temperature is held stable because viscosity is temperature sensitive. The chocolate is filtered again before tempering to remove any remaining lumps that could block depositor nozzles or cause surface defects in molded bars. Tempering is where the bar's final structure is engineered. Cocoa butter can crystallize in multiple forms, but only one dominant form produces the desired gloss, snap, and contraction for mold release. Tempering machines first heat the chocolate to erase existing crystal memory. They then cool the chocolate under agitation to nucleate crystals. Finally, they reheat slightly to melt unstable crystals while leaving stable seeds. The result is a chocolate that remains fluid at working temperature while carrying a controlled population of stable seed crystals. The tempered chocolate feeds molding lines. Molds are cleaned and conditioned so their surfaces are dry and at a controlled temperature. A mold that is too cold can cause premature setting and poor surface finish. A mold that is too warm can slow setting and increase smear risk. Deposit heads meter a precise mass into each cavity. Mass control is essential because bar weight is regulated and because cooling time depends on thickness. After deposit, molds pass over vibrating tables. Vibration removes trapped air bubbles and levels the surface. It also helps the chocolate flow into fine corners and embossed details. Vibration intensity is controlled because excessive vibration can create thin edges and heavy centers. The filled molds then enter a cooling tunnel. Cooling is staged to set the chocolate without creating stress or bloom. The first zone sets the surface quickly to protect shape. Later, zones cool more gradually so the interior solidifies while stable crystals grow. The chocolate contracts slightly as it cools, which creates a gap between the bar and mold wall and enables release. Cooling that is too fast can produce internal stress cracks or a dull surface. Cooling that is too slow reduces throughput and can leave soft surfaces that pick up marks. When the bars reach the release temperature, the molds are inverted or flexed and the bars drop out. Release performance is a sensitive indicator of correct temper. If temper is weak, bars cling to molds and show smeared surfaces. If temper is strong and cooling is correct, release is clean and the surface is glossy. After demolding, bars are conveyed gently to avoid scuffing. Inspection checks can identify broken corners, surface voids, and weight deviations. Bars that fail are diverted to rework streams. Reworked chocolate is remelted and returned upstream because it cannot be reintroduced directly into tempered chocolate without resetting its crystal state. Packaging begins once bars are fully set. Wrapping material is folded around each bar and sealed. Seal temperature and dwell time are controlled so film closes without heating the bar enough to soften the surface. Wrap tension is controlled to avoid imprinting. Codes are printed for traceability and packs are inspected for seal integrity. Bars are then cartoned or case packed for distribution. Maltesers are manufactured by first creating a rigid, hollow, malted honeycomb core that is mostly air, then sealing that fragile core with a thin chocolate layer, then finishing it with a stable outer chocolate coat before cooling, screening, and packaging. Everything starts with the center, because the honeycomb is not molded like a solid candy. It is created by generating gas inside a very hot sugar melt and then freezing that gas structure before it collapses. The center, therefore, needs a syrup that can foam explosively, set fast, and remain dry enough to stay crisp inside chocolate. Sugar is staged as a dry crystal feed and screened to remove clumps that can seed crystallization. Glucose syrup is held warm so it pumps smoothly and helps prevent uncontrolled graining. Malt extract or malt syrup is prepared as its own stream because it brings both flavor and solids and influences viscosity. Water is filtered and tempered because it affects dissolution and cook consistency. A small amount of fat may be included in some systems to control bubble wall brittleness, but the dominant structure comes from sugar glass. The syrup is cooked to a very high solids level. Sugar, water, glucose syrup, and malt components are dissolved and then heated rapidly in a cooker. The cook endpoint is chosen to make a glass that is brittle and sets quickly. If the syrup is too wet, the foam collapses before setting and the honeycomb becomes dense. If too dry, the melt becomes too viscous to expand evenly and can trap large irregular voids rather than a fine network. As the syrup reaches endpoint, it is transferred quickly to a mixing and aeration stage. This stage is designed to incorporate a gas-generating agent at the last moment. The syrup temperature is still high enough to keep viscosity low, but it must not be so high that the agent decomposes too early in the pipework. The gas-generating agent is introduced in a controlled dose, and the syrup is mixed just enough to distribute it without deflating the forming foam. The moment the agent reacts, gas expands through the melt and inflates it into a foam. Expansion is rapid, so the process immediately directs the foaming mass into a casting system. The foam is deposited into trays or onto a belt in a thick slab. The slab rises as gas expands, then begins to set as the melt cools and transitions into a glass. Cooling is engineered to lock the foam architecture. The outer surface must set quickly so the slab holds its height, while the interior must cool enough that bubble walls become rigid. Airflow and plate cooling are used to pull heat out without introducing humidity. Humidity control matters because a fresh honeycomb surface is hygroscopic and will become sticky if it absorbs moisture. Once the honeycomb slab reaches a cuttable brittleness, it is broken down into cores. This is not a clean slicing operation because honeycomb fractures along cell walls. The slab enters a breaker that applies controlled compression to crack it into chunks. The goal is to generate pieces that will later be rounded and sized rather than leaving long jagged shards. The breaker is tuned to minimize powder because honeycomb dust contaminates chocolate and dulls coatings. After primary break, the pieces are sized and shaped. Screening separates oversized chunks, target pieces, and fines. Oversized chunks are returned to the breaker. Fines are removed because they create dust and can clump. The target fraction moves to rounding drums that tumble pieces gently and knock off sharp spikes. Rounding improves coating coverage and reduces punctures that can rupture the chocolate film later. The honeycomb cores are extremely fragile, so conveying is designed with low drops and soft transitions. Vibrations are minimized because they generate dust and fracture. The cores are also conditioned in dry air. Conditioning equalizes temperature and reduces surface tack. It also stabilizes moisture so the cores do not soften before chocolate sealing. Before full coating, the honeycomb is usually sealed. Sealing is a thin chocolate or compound layer that penetrates slightly into surface pores and blocks moisture transfer. Without sealing, the honeycomb would absorb moisture from the chocolate environment and later from the package headspace, losing crispness. Sealing, therefore, acts as a barrier layer and a structural reinforcement. Sealing chocolate is prepared and held at a viscosity that can wet porous surfaces without flooding them. If real chocolate is used, tempering is applied so the seal sets quickly and remains stable. If a compound coating is used, temperature control sets viscosity and set speed. The cores enter a pre-coat stage where they are tumbled while a fine chocolate spray is applied. The spray is light and repeated in several passes because a heavy single application would collapse the honeycomb edges and create thick, uneven spots. After sealing, the cores pass through a short cooling tunnel to set the thin layer. Cooling is tuned to harden the surface while keeping the core dry. Once sealed, the cores can survive the more aggressive motion of full enrobing or panning. The final chocolate coating is applied either by enrobing with a curtain or by panning in rotating drums, depending on the line design. For Malteser's style spheres, panning is often used because it builds an even coat around irregular cores. The sealed centers are loaded into rotating drums, and a measured amount of chocolate is applied in stages. Each stage adds a thin film, and then cooling air sets it before the next film is applied. This staged build prevents the weight of wet chocolate from deforming the fragile centers and prevents pieces from sticking together. Chocolate viscosity and temperature are controlled tightly during coating. Too warm and chocolate becomes thin, runs and pools, leaving uneven thickness. Too cool and chocolate thickens, builds rough surfaces, and fails to flow into small contours. If real chocolate is used, temper control is critical because the coating must set with stable crystals to resist bloom and to provide a clean snap. The coating system therefore monitors temperature and flow resistance and adjusts cooling and heating to keep chocolate in the working range. As coating thickness builds, the process focuses on surface smoothness. Early layers are allowed to penetrate and lock onto the sealed surface. Later layers are applied in thinner films with longer setting time to reduce texture. Drum speed is tuned so pieces roll rather than slide. Rolling distributes chocolate evenly and prevents flats. Sliding creates thin spots and scuffs. Once the coating reaches target thickness, pieces enter a final cooling tunnel. Cooling is staged to avoid stress cracks. The outer surface is set first to protect shape. The interior of the chocolate coat is then cooled gradually so crystals stabilize. Stable cooling also prevents condensation. Condensation causes sugar bloom and surface haze, which is especially visible on smooth chocolate spheres. After cooling, pieces are screened to remove doubles and broken cores. Doubles occur when two pieces stick during a wet stage. Broken pieces shed honeycomb dust and compromise appearance. Screening uses mesh decks sized to the product diameter band. Off-size pieces are diverted. Quality checks focus on core crispness and coating integrity. Crispness is influenced by honeycomb moisture and by seal coverage. Coating integrity is influenced by chocolate temper and cooling. Weight checks confirm coat thickness and core mass remain stable. Visual inspection can detect flat spots and scuffs that indicate coating issues. Packaging begins only after pieces are fully set and at a stable temperature. Warm chocolate will mark and also may release aroma components differently. The pieces are conveyed gently into multi-head weighers. Flow is aided by the spherical shape, but fines can still cause bridging, so dust control remains important. The weigher portions target weights by combining small hopper dumps. Portions drop into bags formed on vertical form-fill seal machines or into cartons depending on format. Seal timing is tuned so chocolate pieces do not lodge in the seal area. Seal integrity matters because moisture ingress will soften honeycomb through the chocolate over time. Packaging films are selected for moisture barrier performance because protecting core crispness is the main shelf life requirement. Case packing and palletizing are designed to limit crushing and temperature swings. Excess vibration creates scuffs. Temperature spikes can soften chocolate and accelerate bloom risk. Stable storage conditions help maintain coating gloss and keep the honeycomb core dry and crisp. The crunch of a Smarties shell is not an accident. It is built one microlayer at a time until a measured thickness of crystalline sugar surrounds a chocolate core and behaves like a small engineered capsule. The process begins by defining the target finished diameter and shell thickness, because those two numbers determine everything else. Once the shell target is set, the center must be manufactured to a diameter band that leaves enough room for the shell to grow without producing oversized pieces. That means the chocolate core is treated as a precision pellet rather than a simple molded chocolate. Chocolate preparation starts with creating a stable suspension of solids in fat. Cocoa components, sugar, and milk solids are blended so powders are evenly distributed. Refining reduces particle size so the chocolate is smooth and so the core surface is dense rather than crumbly. Conching follows to complete fat wetting and remove residual moisture because moisture would later cause texture defects in the shell build. The chocolate is then tempered so cocoa butter forms stable crystals. Temper stability matters here because the core will be tumbled for long periods in rotating pans, and a poorly crystallized core would soften and flatten under repeated impacts. Core shaping is done to achieve a lens profile that rolls predictably. The chocolate is metered in small doses, either into shallow cavities or onto a cooled surface where it can be shaped. Metering controls mass tightly so core weight distribution stays narrow. Shaping controls curvature so the piece does not develop a flat face. Flat faces roll differently and receive shell build unevenly. After shaping, cores are cooled in staged tunnels so they harden without cracking and so their surface remains dry and non-tacky. Before shell building, cores are conditioned. Conditioning brings the cores to a temperature where they are hard enough to resist dents but not so cold that their rims chip and create sharp edges. Rim chipping is a problem because chips become weak points where shells later crack. Conditioning also prevents condensation because any surface moisture would dissolve the first sugar layers and create rough, orange peel textures. Shell building is carried out in rotating pans or perforated coating drums. The cores enter as a rolling bed that must remain in a consistent cascade. Drum fill level and rotational speed are set to create rolling contact rather than sliding. Rolling ensures all surfaces are exposed evenly to syrup and air. Sliding causes flat spots and uneven thickness. The mechanical motion is therefore treated as a controlled input in the same way as syrup concentration. The first shell layers are designed as a bonding bridge. A light syrup is atomized into very fine droplets and sprayed in short pulses. Droplet size is kept small so it spreads thinly and does not pool. Immediately after each pulse, drying air flows through the bed and removes water so a crystalline film forms at the surface. This early stage must be fast setting to prevent pieces from sticking together and forming twins. It must also be gentle enough not to soften the chocolate core. Once adhesion is established, the process switches to thickness build cycles. A higher solid syrup is applied, then fine sugar is introduced as a dust. The dust absorbs moisture from the syrup film and accelerates crystallization. Drying air then removes remaining water and strengthens the new layer. This spray dust dry sequence is repeated many times. Each individual layer is thin because thin layers crystallize more evenly and reduce internal stress. Thick layers dry unevenly and create trapped moisture pockets that later pit or crack. Drying conditions are tuned continuously. Air temperature must be high enough to evaporate water efficiently, but not so high that it warms the chocolate core and risks deformation. Air humidity must remain low enough to pull moisture out, but not so low that the surface hardens instantly and traps water inside the shell. The process balances these factors, so crystallization progresses through the layer thickness rather than forming a hardened skin on top of a damp interior. As the shell thickens, the sound and motion of the bed change. Pieces become harder and collision noise becomes sharper. The process compensates by adjusting drum speed slightly to maintain rolling without excessive impact. Too much impact at this stage chips edges and creates exposed shell layers. Too little impact produces irregular shapes and non-uniform thickness. Near the target thickness, the focus shifts to smoothing. Dust addition is reduced because dust tends to leave a rough micro texture. Instead, thinner syrup films are sprayed and given longer drying time. Thin films flow into micro valleys and reduce ridges created during bulk build. This is also where roundness improves because mild abrasion during tumbling knocks down high points and helps the shell approach an even curvature. Color application is treated as a separate operation, layered on top of the structural shell. Color solutions are prepared to precise concentration and filtered to remove undissolved particles that could create specks. Color is applied in multiple light coats rather than one heavy coat. A light coat wets the surface uniformly and dries quickly without pooling. Pooling creates blotches and uneven shade. Between coats, drying air sets the film completely so the next coat does not dissolve the previous one. Color is typically introduced when the shell has reached most of its thickness but still has enough surface receptivity for good adhesion. Introducing color too early risks burying pigment under later clear layers and muting shade. Introducing color too late risks weak adhesion and rub-off because the surface can be too hard and slick. The process therefore schedules color passes within a window where the surface still accepts thin films but the shell is strong enough to tolerate extra handling. Because multiple colors are produced, color runs are separated to prevent cross tint. Spray lines are flushed between colors and pans are cleaned so residue does not contaminate the next batch. Shade is checked with optical measurement and adjusted by adding additional light passes or altering concentration within a narrow range. Uniform shade depends on maintaining consistent bed motion and consistent droplet size because any change in wetting pattern shows as streaks. After color, a protective finish layer is applied. This can be a clear syrup coat that locks pigment and reduces rub-off. The clear coat is applied sparingly to avoid creating a sticky surface. It is followed by extended drying so moisture reaches a stable endpoint. Moisture endpoint determines both crunch and handling. Too much moisture makes shells tacky and prone to scuffing. Too little moisture makes shells brittle and prone to chipping during conveying. Moisture equalization follows drying. Even when the surface feels dry, the inner shell can retain slightly different moisture. Equalization holds the candies in controlled air so gradients flatten. This reduces internal stress that can cause fine hairline cracks and improves shelf stability. Polishing is the final surface engineering step. A very small amount of polishing agent is misted into a polishing pan while pieces tumble gently. The film spreads across the shell's surface and fills micro pores, increasing gloss and reducing friction. Reduced friction improves flow through hoppers and reduces scuffing in packaging. Polishing is controlled carefully because excess polish can feel waxy and can reduce the crisp sensory perception of the shell. If a printed mark is used, it is applied after the surface is smooth and dry. Printing uses edible ink transferred by a pad system. Pieces are fed and oriented so a stable face is presented. The pad picks up ink from an etched plate and stamps it onto the shell. Ink viscosity and pad pressure are tuned so the mark is crisp without smearing. A short drying stage sets the ink before pieces are mixed and conveyed. Sorting and sizing occur before packaging. Screens remove fines and broken fragments. Optical sorting removes twins, chipped shells, and off-color pieces. Size classification removes pieces outside the diameter band because off-size pieces disrupt appearance and affect weigher accuracy. Sorting also protects packaging because irregular pieces can bridge or jam. Conveying is designed to minimize impact. Drop heights are kept low and chutes are smooth and curved. Hoppers are steep and low friction to maintain flow without heavy vibration. Excess vibration increases abrasion and creates dust that dulls gloss and contaminates seals. Packaging starts with portioning. Multi-head weighers distribute candies into multiple hoppers and select combinations that meet the target weight precisely. Accurate portioning depends on consistent piece size and free flow. The portion drops into a bag formed by a vertical form-fill seal machine or into a carton fill funnel depending on format. Seals are made while keeping candies away from the seal zone because trapped pieces or sugar dust can create leaks. Mentos start as a controlled balance between dry crystals and warm syrup. The goal at the beginning is simple. Create a base that can be shaped without cracking, and then set it into a stable chew that will accept a hard shell. Sugar enters the line first, and it is treated as an engineered material rather than a sweetener. The crystals are screened so the size range is tight. That matters because the later mixing stage relies on predictable wetting. When crystal sizes vary too much, the small particles hydrate fast, and the large particles stay dry. That creates weak zones that show up as gritty texture or uneven bite. In parallel, a glucose-based syrup is held at a steady temperature in jacketed tanks. The heat keeps the syrup flowing like a thick liquid instead of a slow gel. Pumps push it through filters and meters that smooth out pulsations. The entire point is to deliver the same flow every second. If the syrup surges, the candy core becomes soft. If it starves, the core becomes crumbly. Dry minor ingredients join through feeders that behave like precision valves. Texturizers such as starch are added to control stickiness during forming. Acidulants are added to tune brightness and to steer how the sugar phase behaves during conditioning. Very small additions are blended upstream so they do not land as streaks in the mass. The streams meet inside an enclosed mixer, where wetting is forced to happen quickly. paddle elements sweep the walls and fold the mass through itself. The mixture passes through stages that look like dry sand at first and then like damp granules. As mixing continues, the granules begin to bind. The syrup coats the crystals and bridges them into a cohesive feed for the next machine. From the mixer, the material enters a continuous conditioner. This is where heat and shear begin the real transformation. The mass is kneaded while the temperature rises in controlled steps. Some of the sugar dissolves into the syrup phase. The remaining crystals stay intact and act like structural filler. That blend is what gives the final core its specific chew. Too much dissolution makes a rubbery bite. Too little dissolution makes a brittle bite. A vacuum section often follows to pull out trapped air. Air pockets are small, but they matter. They create internal voids that can collapse during coating. They also reduce density, which changes how pieces roll in later drums. When the air is removed, the mass becomes smoother and more uniform. Next comes forming, and this is where the process starts to look like candy rather than paste. The plasticized mass is pushed through a die to create a continuous rope. The rope has a defined diameter that matches the final piece width. A set of rollers or calibration guides controls the rope's surface so it does not twist or flatten. The rope moves directly into a cutting unit that portions it into pellets. The cut timing is locked to belt speed, so every piece has the same length. The cut faces are still fresh and slightly tacky. That tack is useful because it allows the next step to round the shape without cracking the surface. The pellets enter a rounding stage where they tumble and roll against each other. The motion knocks off sharp edges and forces the surface to smooth. Friction warms the outer layer just enough to seal micro cracks. The goal is a dense core with a consistent geometry. That geometry is critical because the shell builds evenly only when each core rolls the same way. After shaping, the cores must be conditioned before coating. They travel through controlled air sections that adjust temperature and moisture. This step prevents shell defects later. If the core is too warm, the first shell layers dissolve and smear. If the core is too dry, the first layers do not bond well. Conditioning brings the cores to a stable state where the surface is firm yet receptive. When the cores reach coating, they enter large rotating pans or perforated drums. The core movement is constant and it is carefully tuned. The bed depth and rotation speed control collisions. Collisions must be strong enough to keep pieces separated. They must not be so strong that they chip the still forming shell. The shell is built in layers rather than one application. A coating solution is sprayed as a fine mist across the moving bed. Immediately after spraying, a dry powder is often dusted in. Airflow then removes moisture, so the layer sets before the next one arrives. This spray and dry cycle repeats many times. Each cycle adds only a thin film. Layering avoids cracks because stress is distributed gradually. At the start of coating, the syrup phase is more forgiving. It acts like an adhesive primer that locks onto the core surface. As cycles continue, the composition shifts toward harder, sugar-based layers. The process gradually moves from bonding to building. The shell thickens and becomes the structure that gives the candy its snap. Drying is not just about removing water. It is about controlling how crystals form. Fast drying can trap moisture inside and create a brittle outer skin. Slow drying can let the surface stay tacky and cause pieces to stick together. The airflow temperature and humidity are tuned, so crystallization happens evenly through the growing shell. As thickness increases, the process focuses on smoothness and roundness. The spray pattern is adjusted so no side gets more liquid than another. The drum motion is adjusted so pieces roll rather than slide. Rolling is what builds a uniform shell. Sliding creates flats and ridges that later show up as rough mouthfeel. Color and flavor can be introduced at specific points in the shell build. Early addition drives deeper penetration into the outer layers. Late addition keeps aroma closer to the surface. Timing is used as a control knob. It shapes how quickly the flavor is released when the candy is chewed. Once the shell has reached its target mass, the finish steps begin. A final smoothing phase uses lighter sprays and longer dry time. This reduces micro texture and tightens gloss. Then a polishing agent is applied in a thin film. The agent spreads under tumbling and fills tiny surface pores. The result is a clean shine and reduced friction, so pieces do not scuff in handling. The coated candy now needs final equilibration. It is held in bins or conditioning rooms where moisture equalizes between core and shell. This reduces internal stress. Without this step, the shell can craze. Crazing looks like fine cracks, and it can grow during storage. Quality checks happen along the line. But the main process signals are physical. Size distribution is checked because coating mass depends on surface area. Shell thickness is checked because it controls crunch and dissolution rate. Hardness is checked because it reflects both moisture and crystal structure. Surface inspection looks for chips and twins. Twins are two pieces stuck together during coating. When the product is cleared, it moves to packaging. The candy is conveyed to weighers that portion exact amounts. The flow properties matter here too. The polished shell helps the pieces slide and settle. Multi-head weighers use many small hoppers to assemble a target weight with minimal deviation. The measured portions drop into form-fill seal machines or cartoning systems depending on format. Film is formed into a tube and sealed. The drop is timed so pieces fall cleanly without crushing. Seals are made with controlled heat so the film closes without wrinkles. If cartons are used, the candy is fed into inner packs and then into outer sleeves. Nerd's Candy is built by turning concentrated flavored sugar syrup into a porous sheet, then fracturing that sheet into tiny irregular crystals, then sorting and finishing those crystals so each piece stays sharp and dry. Production starts with raw sugar management because particle size and purity drive how the syrup cooks. Granulated sugar is conveyed from bulk storage into day bins that feed the dissolving system. Screens remove oversized crystals and fines to keep dissolution predictable. Magnets and strainers protect downstream pumps and valves from metallic debris. A second carbohydrate stream is prepared to control viscosity and inhibit unwanted crystallization during cooking. Corn syrup is warmed in jacketed tanks until it reaches a stable pumping consistency. Flow meters and control valves keep corn syrup delivery steady across the run. Water is filtered and tempered so it enters mixing at a consistent temperature. Dry acids are staged in sealed hoppers so they remain free-flowing. Citric acid and malic acid are kept separate until late addition because acid affects inversion and color stability. Salt and buffering salts are staged in microfeeders when the recipe calls for them. Flavor concentrates are prepared in small tanks with controlled agitation so they stay homogeneous. Color solutions are diluted to a dosing range that avoids banding and streaking. The line splits early into two parallel syrup paths because Nerds typically pairs two flavors and two colors. Each path has its own dissolving and cooking controls, even if both share utilities. This separation lets each flavor reach its own target acid and aroma level without compromise. Sugar dissolution begins in a heated dissolver where sugar and water form a high solid slurry. Agitators sweep the vessel walls to prevent sugar crust. The slurry is heated until it becomes a clear solution. Inline strainers remove undissolved particles that would seed crystals too early. The solution flows to a balance tank that evens out feed rate to the cooker. Concentration is driven by a continuous cooker that raises temperature and removes water. Many lines use a coil or plate heat exchanger, followed by a flash stage. The syrup enters under pressure so it can reach high temperature without boiling. The flash section drops pressure and releases water vapor in a controlled burst. This step tightens final moisture and improves consistency. Bricks and temperature are monitored constantly because small shifts change how the candy fractures later. A higher final moisture yields a tougher sheet that breaks into larger chunks. A lower final moisture yields a brittle sheet that shatters into dust. The target sits in a narrow window that supports clean fracture with limited fines. Corn syrup is injected at a controlled point to tune glass transition and reduce uncontrolled graining. The injection location matters because early addition changes cook behavior. Late addition can preserve more of the corn syrup function as a plasticizer. The syrup then passes through static mixers that eliminate streaking. Acid addition is handled carefully because acid can catalyze sucrose inversion during heat exposure. Many processes add acid after the hottest zone to limit inversion. The acid is metered as a solution to ensure rapid dispersion. Inline pH measurement is used in some lines as a confirmatory control. This stage sets the tart backbone that defines the flavor profile. Flavor and color are added after temperature is reduced to protect volatile compounds. A cooling loop drops syrup temperature to a range where aromas survive. Flavor oils are dosed through precision pumps into a turbulent region. Emulsifiers may be included, so oil-based flavors stay evenly distributed. Color is injected with high shear mixing, so each path produces uniform hue. The two flavored syrups now need to become solid candy in a form that can be fractured. One common approach is slab casting or film casting onto a cooled surface. The syrup is deposited as a thin ribbon onto a moving stainless belt. Belt speed and deposit rate set film thickness. Cooling plates beneath the belt pull heat out rapidly and evenly. As the film cools, it becomes a glassy sheet rather than a soft mass. Rapid cooling prevents large crystals from forming. The goal is an amorphous structure with controlled microcrystallization later. The sheet is guided through a cooling tunnel where air temperature and velocity are controlled. Surface moisture is kept low, so the sheet does not pick up tack. Some processes encourage controlled graining after initial set. This can be done by seeding or by mechanical working. Light agitation or flexing creates internal stress sites that guide fracture. The sheet may pass through a scoring station that introduces shallow grooves. Grooves create predictable breakpoints and reduce random oversized lumps. Once the sheet reaches a target, brittleness, it is released from the belt. A scraper blade lifts the sheet edge and directs it into a breaker. The breaker uses toothed rollers or oscillating bars to crack the sheet into pieces. The first break aims for chips that are still larger than the final candy size. This staged reduction avoids excessive dust creation. The chips move into a milling and crushing system that creates the nerd's granule size. A common setup uses roll crushers that apply compressive force. Roll gap controls the size distribution and also controls the amount of fines. Too tight a gap makes powder and reduces yield. Too wide a gap leaves chunks that do not feel like nerds. After roll crushing, the material enters a vibrating screen deck. Screens separate into multiple fractions in one pass. The target fraction is routed forward as product stream. Oversize is returned to the crusher for another pass. Fines are collected as a separate stream for rework or controlled reuse. The system is tuned to make irregular shapes rather than uniform spheres. Irregular shapes create the characteristic crunchy texture. The fracture surfaces must remain sharp and dry. Rounded surfaces would suggest coating that is too heavy or milling that is too aggressive. Because nerds often includes two flavors. In one pack, the line must keep colors separated until final blending. Each flavor color runs through its own crushing and screening loop. This prevents color contamination in recycle streams. It also allows each flavor to use its own target brittleness. Some flavors require slightly different moisture to break cleanly. Once each color is sized, it moves into conditioning bins. Conditioning allows moisture gradients to equalize inside each granule. Equalization reduces later caking in storage. It also stabilizes crunch by keeping the candy in a glassy state. Airflow in these bins is controlled to prevent humidity pickup. At this stage, the candy may receive a very light finishing step to improve flow. A tiny amount of anti-caking agent can be applied as a dry dust. The goal is to reduce surface stick points without changing texture. Application is done in a tumbler where powder distribution becomes uniform. Excess powder is removed by aspiration, so the finish remains minimal. Some formats use an additional micro-coating for color stability or acid placement. This can be done by misting a dilute syrup and then drying quickly. The mist acts as a binder for a fine acid layer or a color adjust layer. Drying must be fast so the granules do not fuse together. The micro-coating is kept thin to avoid rounding edges. If the recipe calls for a stronger sour hit, the acid can be partially surface loaded. Surface loading is done after sizing so the acid stays near the exterior. This approach changes perception because acid dissolves immediately. It also requires careful humidity control because acids can pull moisture. Granules are then blended to match the intended mix ratio. A gravimetric. Blending system meters each color stream. The blender uses gentle paddles or ribbon elements that avoid crushing. The objective is homogeneous distribution without generating new fines. Sampling at the blender outlet confirms color ratio across time. Transfer to packaging requires stable flow behavior. Granules can bridge if humidity rises or if fines increase. Hoppers are designed with steep walls and vibration options. Feed screws or vibratory feeders deliver candy into multi-head weighers. Weighers build target weights by combining small hopper dumps. Packaging format changes the final handling steps. In small boxes, the granules drop into cartons through a funnel system. Carton fill height is controlled to avoid crushing at the edges. In bag formats, the candy drops into a forming tube and then into sealed film. Seal timing is synchronized with the drop to keep granules out of seal areas. Some products use dual chamber packaging that keeps flavors separated until pouring. Dual chamber designs require two parallel weigh and fill lanes. Each lane fills its own side of the package. A split forming collar shapes the film into two channels. Seals create a central divider that remains intact. For mixed packs that combine two flavors in one cavity, the blender feeds a single weigher. The weigher controls portion size and drop accuracy. Drop height is minimized to reduce fragmentation. Chutes are designed with low friction surfaces to prevent hang-ups. Coding and inspection happen after sealing and closure. Vision systems can verify fill presence and detect seal contamination. Weight checks confirm package mass within tolerance. Reject systems remove outliers without stopping the line. Finished units are then collated into cases. Case packing is designed to limit vibration that could create dust. Cartons or bags are grouped and then dropped into corrugated cases. Cases are closed and sealed with tape or adhesive. Pallet patterns are chosen to reduce compression on lower layers. Skittles candy is made by building a chewy flavored center and then growing a crisp sugar shell that carries color and gloss. The process is a long chain of controlled transformations. It begins with dry powders and syrups that are treated like engineering feedstocks. It ends with uniformly sized pellets that flow through packaging equipment without sticking. The first stage is ingredient staging and metering. Granulated sugar is unloaded into silos and routed through screens that narrow the crystal size range. Consistent crystal size keeps dissolution predictable during cooking. Glucose syrup or corn syrup is held in heated tanks so it can be pumped at a stable flow rate. Water is filtered and tempered so it enters the system at a repeatable temperature. Minor ingredients are staged in sealed bins and then moved to microfeeders. These microfeeders meter acids and salts and functional powders with high precision. The center of a Skittles piece starts as a cooked candy base that will later be plasticized into a chew. Sugar and water first meet in a dissolving system that prevents dry clumps. Agitators create a strong vortex and pull crystals into solution. Heat raises the mixture to speed dissolution while avoiding localized scorching. The goal is a clear syrup with no undissolved grains. Inline strainers remove stray solids that could seed crystals later. The syrup then flows into a balance tank that smooths out any upstream fluctuations. From the balance tank, the syrup feeds a continuous cooker. The cooker raises temperature quickly to drive off water and concentrate solids. Many lines use pressurized heating, so the syrup can reach high temperature without boiling in the coil. After heating, the syrup enters a flash stage that drops pressure. Water vapor leaves instantly and pulls heat out at the same time. This step locks in final solids content and sets the base viscosity for the next stages. Solids content is tracked constantly because it affects chew texture and forming behavior. If moisture is too high, the centers stay soft and can deform during shell building. If moisture is too low, the centers become brittle and can crack under tumbling loads. Temperature is controlled with tight limits because viscosity changes rapidly with heat. Flow meters and control valves keep feed rate steady because residence time in the cooker must remain stable. After concentration, the hot syrup is cooled to a controlled temperature before sensitive ingredients are added. Cooling happens in a scraped surface exchanger or a plate heat exchanger. Scraped surfaces are used when viscosity is high and fouling risk increases. The cooled syrup enters a mixing manifold where functional additions are injected. Acids are added at this stage to manage flavor brightness and to set the target pH. Adding acid after the hottest zone reduces unwanted sucrose inversion. Flavor addition is handled as a separate system because flavors can be volatile and unevenly dispersing. Oil-based flavors are prepared as emulsions or are blended with carriers. Water-soluble flavors are diluted to a pumpable concentration. Both are dosed through metering pumps into a turbulent section of the stream. Static mixers fold the flow repeatedly to eliminate streaks. The objective is to make every portion of the candy base taste identical within a batch. Color is not usually placed in the center for a classic Skittles style. The center can remain neutral or lightly tinted depending on product type. This choice keeps the center stable and lets the shell carry the signature color identity. Even when the center is neutral, it must still be consistent in density and moisture. That consistency keeps shell growth uniform and prevents weak adhesion areas. The cooked and flavored mass now moves into a forming system. At this point, the material behaves like a thick plastic melt. It must be shaped into small pieces that will become the final candy cores. Extrusion is a common forming method for this kind of center. The mass is pushed through a die plate to create multiple ropes at once. Each rope has a controlled diameter that matches the planned final piece size after shell growth. As the ropes exit the die, they are cut into pellets. Cutting uses rotating knives or wire cutters synchronized to line speed. The cut length defines the initial core mass. Tight control is critical because shell thickness is added on top of the core. If core mass varies, then final piece mass varies, even if shell growth is perfect. The freshly cut pellets are soft and tacky. They must be conditioned quickly so they do not fuse together. Pellets transfer to a preconditioning conveyor or a cooling drum. Cooling air removes surface heat and firms the outer layer. The cooling profile is chosen to avoid a hard skin with a soft interior. A hard skin can crack during tumbling and expose a sticky interior. A uniform set keeps the pellet resilient during handling, The pellets may pass through a light dusting stage that prevents sticking. The dust is minimal and it is chosen to avoid changing flavor. Shaping continues with rounding. Pellets tumble in a rotating drum where they collide and roll. The motion rounds edges and smooths cut faces. Friction and gentle compression help the surface seal. The goal is a compact core with a slightly elastic bite. This elastic bite is what defines the chew under the later crisp shell. Rounding also improves how pieces roll in coating pans. Uniform rolling produces uniform shell thickness. After rounding, the cores undergo a rest stage. Rest allows moisture and temperature to equilibrate through the core. This reduces gradients that can cause deformation later. The cores move through conditioning bins with controlled airflow. Air temperature and humidity are adjusted so the core surface becomes dry enough for coating adhesion without becoming brittle. Moisture content is measured or inferred from process correlations. The process aims to keep the core in a stable glassy or rubbery state depending on formulation. Now the line transitions into shell building. Shell building is where Skittles develops its hard, crunchy outer layer. The cores enter large rotating coating pans or perforated coating drums. Rotation makes the bed of cores circulate in a continuous wave. Cores climb and then slide or roll down the moving bed. That rolling action exposes all surfaces to spray and to drying air. Shell growth happens in cycles. Each cycle applies a thin layer of syrup and then removes water to crystallize that layer. A spray system atomizes a sugar solution into a fine mist. Droplets land on moving cores and form a wet film. Almost immediately, dry air flows through the bed to evaporate water. As water leaves, the dissolved sugar crystallizes and locks into a solid layer. The drum continues rotating, so pieces do not stick to each other while wet. Hard candy only has two useful states on a lollipop line: fluid enough to be shaped and glassy enough to hold its shape. Chupa Chups style production is built to push the candy through that transition at the exact moment a stick is inserted and locked, then isolate the finished piece from humidity so it never leaves the glassy state. The most reliable way to understand the factory is to start at the forming wheel, because every upstream system exists to feed that wheel at a stable rhythm. The forming wheel is an indexed machine with cavities that open, receive a dose of hot candy, accept a stick close to shape, then release the lollipop. Its speed is fixed by output targets, so the candy mass must arrive at the depositor at the correct temperature and viscosity, and sticks must arrive at the inserter in the correct orientation and at the correct moment. Stick handling runs continuously. Sticks are cut to length if not pre-cut, then screened to remove splinters. A deburring or air cleaning stage strips dust because dust at the interface weakens bonding and creates voids. Sticks are then singulated into individual lanes. Singulation is a mechanical sorting problem. Sticks are light and can overlap, so feeders rely on vibration, step conveyors, and guide rails to separate them. Orientation is enforced, so the same end enters the candy each time. The stick feed ends at a pick-and-place head or pusher that inserts the stick into the cavity at a fixed depth. Depth stops are mechanical, so insertion depth remains consistent even if stick length varies slightly. Depth matters because too shallow reduces pull strength, and too deep can create internal stress rings that lead to cracking. While sticks are being fed, the candy mass is being prepared as a concentrated syrup that will set into a clear glass. Sugar is stored dry and screened so clumps do not enter dissolving. Water is filtered and tempered because inlet temperature affects dissolution speed and cook stability. Glucose syrup is held in jacketed tanks so viscosity stays stable for pumping, and it functions as a crystallization control ingredient. These streams combine in a dissolver, where heat and agitation create a clear solution. The target is full dissolution with no visible grains, because undissolved grains become nucleation sites that can trigger graining later, making the candy cloudy and brittle in an unpredictable way. Concentration is performed rapidly to reach hard candy solids. In a continuous system, the clear syrup is pumped through heated coils under pressure, allowing temperature to rise quickly without boiling inside the tube. A flash chamber then reduces pressure so a portion of water instantly vaporizes and exits as steam. This flash step tightens final moisture and also reduces thermal damage because water removal occurs at a lower effective temperature than extended open boiling. Final moisture content is the main structural setting. Too much moisture yields candy that stays tacky and softens quickly. Too little moisture yields candy that becomes overly brittle and cracks at the stick interface during cooling or later handling. Immediately after concentration, the mass enters a controlled cooling section. The aim is to bring the mass to a forming temperature that is still fluid enough to be deposited and shaped, but not so hot that it degrades flavor and not so cool that it begins to set in pipes. Heat exchangers and jacketed manifolds manage this temperature precisely. At this stage, additives are introduced because many flavors contain volatile compounds that would be stripped or damaged at peak cooking temperatures. Color is prepared as concentrated solutions or dispersions and filtered so no particles clog injectors or create specks. Flavor is metered by precision pumps into the candy stream. Injection is placed after the main heat load so aromatics are preserved. Acid can be introduced as a solution if the recipe calls for a sharper profile, but acid timing is controlled because acid accelerates sucrose inversion at high temperature, which changes viscosity and long-term stickiness. Mixing after injection is done with static mixers or low-shear mixing manifolds that fold the flow and eliminate streaks without entraining air. Air entrapment is undesirable because bubbles create weak zones and can appear as surface pits once the candy cools. The candy mass then feeds the depositor at the forming wheel. The depositor meters a precise amount into each cavity. Portion volume directly sets lollipop size and weight. Metering is done by piston pumps or gear pumps synchronized to the wheel index. Dose accuracy matters because a low fill yields thin spots and poor stick anchoring, while an overfill creates flash that must be trimmed and increases wrapper puncture risk. The cavity receives the candy dose first or simultaneously with stick insertion depending on machine design. In one approach, the cavity is partially filled, then the stick is inserted, then a second small dose tops off and the cavity closes. In another approach, the cavity closes on a measured candy slug and the stick is driven into it. The common requirement is that candy must be plastic at the moment the stick enters, so the candy wets the stick surface and bonds as it cools. Shaping occurs when the cavity closes. The closing motion forces candy into the spherical geometry and expels trapped air. Venting channels can allow small air pockets to escape so they do not remain as bubbles. Cavity surface finish is polished, so the candy skin releases cleanly. Cavity temperature is managed so candy does not stick or smear. If cavities are too cold, the candy skin sets instantly and can trap air. If cavities are too warm, the candy remains tacky and can deform during demolding. The machine therefore maintains a stable mold temperature through internal circulation. As the formed lollipop exits the cavity, it is still hot enough that the interior is not fully glassy. It immediately enters a cooling system that locks structure. Cooling is staged. The first stage sets the outer surface quickly so the shape stops flowing. This can be done with cool, dry air directed at the candy surfaces. The second stage brings the core temperature down so the entire mass crosses into the glass state. Cooling rate must be controlled because excessive thermal gradients create stress. Stress tends to concentrate around the stick insertion zone because the stick acts as a rigid inclusion and the candy contracts around it. If the outer layer contracts much faster than the inner, microcracks can form. These cracks may be invisible initially, but can propagate during shipping or when humidity changes. Humidity control in cooling is essential. Hard candy absorbs moisture from air. If cooling air is humid, a thin moisture film can form on the warm candy surface. This film dissolves sugar at the surface and then recrystallizes as a rough haze, reducing gloss and increasing stickiness. Cooling tunnels therefore use dry air. Some lines control dew point directly, keeping dew point low enough that condensation cannot form on the candy at any point in the tunnel. Once cooled to handling temperature, lollipops are demolded or released from the forming wheel and transferred to conveyors. Transfer points are designed to avoid impact at the candy head because the surface can still mark if it is too warm. Guides support sticks rather than candy heads because contacting the head can create flat spots. The lollipops pass through inspection and rejection systems. Vision systems can detect off-center sticks, incomplete fill, surface bubbles, and flash around seams. Weight checks can detect underfill and overfill. Reject mechanisms remove defective pieces before wrapping because wrapping a defective piece wastes film and creates downstream jams. Twizzlers are manufactured by converting a cooked sweet base into a plastic, elastic candy dough, shaping that dough continuously through extrusion, setting texture through staged drying and cooling, then cutting and wrapping so the ropes stay chewy and separate without sticking. The most useful place to start is the cutter, because the cutter reveals whether the upstream dough has the right cohesion and whether the rope has been set enough to hold its geometry. If the rope tears at the cut, the dough is underhydrated or too cold. If it smears and strings, the dough is too warm or too wet. The factory therefore tunes the entire process to deliver an extrudate that behaves predictably at the knife. Upstream of the cutter, the rope travels through setting tunnels that control moisture and temperature. Those tunnels are what convert an extruded ribbon into a stable Twizzler's rope with a uniform chew. The rope exits the die warm and pliable, and its interior still contains enough water to make it sticky if packaged immediately. The setting tunnel removes a measured amount of moisture while allowing the matrix to equilibrate so the surface becomes dry enough to handle, yet the core remains chewy. Air temperature, humidity, and velocity are balanced to avoid case hardening. Case hardening creates a tough outer shell and a soft interior, which leads to cracking during bending and an uneven bite. Staged zones, warmer early zones, and gentler later zones reduce that risk. Before the rope ever reaches those tunnels, the line creates the candy dough in a cooker and mixer system designed for high solids. Sugar and glucose syrup are staged as the main carbohydrate system. Granulated sugar is screened to remove clumps and dust because clumps dissolve unevenly and dust can scorch at hot surfaces. Glucose syrup is held in jacketed tanks so viscosity stays stable for metering. Water is filtered and tempered because inlet temperature shifts dissolution and cook stability. Starch and other structure-building solids are held dry and fed accurately because their hydration rate determines dough firmness later. Cooking starts in a dissolver where sugar is hydrated into a clear solution. That solution then moves to a cooker where heat drives off water and raises solids. The cook endpoint is selected so the base becomes plastic when cooled, not glassy like hard candy, and not fluid like syrup. The endpoint is typically controlled by temperature and by flow resistance in the cooker. If the base is undercooked, it carries too much water and produces a sticky rope that never sets. If overcooked, it becomes too stiff, causing high extruder pressure and surface cracking at the die. After cooking, the hot base is cooled into a window where powders can be incorporated without clumping, and flavors can be added without being stripped. At this stage, the line transitions from a boiling syrup process to a dough making process. Structure formers, like starches, must be dispersed and hydrated evenly. Dry starch added directly to hot syrup would form lumps with dry cores. To avoid that, starch can be fed through high shear mixers or introduced as a slurry that is hydrated and cooked separately before blending. The goal is a continuous matrix where starch and sugars form a cohesive network. Acids and salt are staged as low-rate additions. Acid influences flavor and also changes the behavior of the carbohydrate matrix over time by shifting inversion and hygroscopicity. For that reason, acids are added after the hottest zones and mixed thoroughly but gently. Flavor and color are also added late. Flavor injection is done downstream of intense heat to preserve volatile components. Color is metered as a concentrated solution to avoid adding excess water. Once all components are combined, the mass enters intensive mixing. This is where it becomes a uniform plastic dough. The mixer uses high torque elements that fold and shear. Shear must be sufficient to eliminate streaks and fully wet powders. Shear must not be so aggressive that it whips air into the dough, because trapped air causes bubbles and weak spots in the extruded rope. Mixing endpoint is judged by uniform color, uniform torque, and a stable temperature. Temperature is monitored continuously because the dough must remain plastic but not overly soft. The dough then enters a conditioning stage before extrusion. Conditioning equalizes moisture throughout the mass and stabilizes temperature so extrusion pressure does not pulse. This can be done in a holding hopper with gentle agitation or in a screw conveyor that provides a fixed residence time. The objective is to deliver the extruder a steady feed that produces a steady rope diameter. Extrusion is the primary shaping method. The dough is fed into a screw extruder whose barrel is temperature controlled. The screw compresses and pushes the dough forward. Compression removes minor voids and increases cohesion. Barrel temperature keeps the dough in the plastic range. If the barrel is too cool, pressure rises and the rope surface becomes rough. If too warm, the rope surface becomes tacky and can collapse after exiting the die. The die defines rope, cross-section. Twizzlers ropes are typically round or slightly shaped, depending on the product format. Die temperature is controlled because cold dies cause surface tearing and hot dies cause smear. Pressure at the die is monitored. It acts as an indicator of dough viscosity and hydration. Stable pressure produces stable diameter, which matters because diameter controls final chew and package weight. Immediately after extrusion, the rope is guided by takeoff belts. Belt speed must match extruder output to avoid stretching. Stretching thins the rope and aligns the matrix, which can make the bite tougher and can produce uneven twist definition. The rope is supported so it does not sag, because sag introduces diameter variation and can cause twists to tighten unevenly. Twist formation, when used, is produced by controlled rotation relative to forward motion. A twisting head grips the rope or imparts rotation while the takeoff belt pulls. The twist pitch is set by the ratio of rotational speed to linear speed. A tighter pitch yields a more pronounced twist and slightly denser bite. A looser pitch yields a smoother rope and a softer feel. Twist must be consistent along the rope, because variation creates weak points where the rope can split during cutting or packaging. After twisting, the rope enters the staged drying and cooling tunnels described at the beginning. These tunnels are engineered to hit a final moisture endpoint that supports chew without stickiness. Early tunnel zones focus on removing surface moisture so the rope can be handled without clumping. Later zones allow moisture to migrate from the core to the surface gradually and leave the rope at a stable water activity. Airflow is controlled to avoid whipping ropes into each other, and the rope is kept separated by lane guides. Once the rope reaches the target set, it passes to cutting. Cutting uses rotary blades, or guillotine cutters, synchronized to belt speed. Synchronization controls piece length and therefore piece weight. Blade sharpness is managed because a dull blade drags and creates strings at the ends. Stringing is a sign that the rope is still too warm or too wet. A clean cut indicates the surface has set and the interior has enough cohesion to fracture neatly at the blade. Cut pieces then go through a short post-set stage. This allows freshly cut ends to dry slightly so pieces do not stick end to end. It also allows any residual heat from cutting friction to dissipate. If a light surface treatment is used to improve flow, it is applied here. A tiny amount of neutral oil can be misted while pieces tumble gently. The oil film reduces surface friction and helps prevent sticking in the wrapper. Oil application is minimal because excess oil changes mouthfeel and attracts dust. Screening can follow to remove fragments created during cutting and conveying. Removing fragments improves pack appearance and reduces dust that can interfere with seals. Metal detection or other final integrity checks can be positioned here because product flow is stable and pieces are separated. Wrapping begins with controlled feeding into flow wrappers. Pieces are aligned into lanes and spaced, so each wrapper cycle receives one piece. Film is formed around the rope and sealed with heat and pressure. Seal dwell and temperature are tuned, so seals are strong without overheating the candy surface, because overheating can soften the rope and deform it under film tension. Film tension is controlled so it sits snug without squeezing the rope flat. Slush. Puppy-style slush is manufactured by producing a shelf-stable flavored concentrate, then engineering a dispensing system that freezes a diluted beverage into a suspension of tiny ice crystals without forming a solid block, then keeping those crystals moving so the product stays scoopable and uniform in a cup. The easiest way to understand the production chain is to start at the point of consumption, the slush machine. A slush machine is essentially a controlled, scraped surface freezer that must keep a mixture right at its freezing curve. It needs enough sugar and solutes to depress the freezing point, enough viscosity to keep ice crystals suspended, and enough agitation to prevent large crystals from growing. Everything that happens in the factory is designed to make a concentrate that, when diluted, behaves correctly inside that machine. The slush machine relies on a mix ratio that is tightly defined. The concentrate is not used full strength. It is diluted with water to a target sugar concentration. If the mix is too weak, freezing point rises and the machine produces a hard ice mass or large crystals that separate into watery and icy zones. If the mix is too strong, freezing point drops too far and the machine struggles to freeze enough, yielding a cold syrup rather than slush. That is why the factory builds the concentrate with a known soluble solids level and a known acidity, and why it specifies a dilution ratio. Concentrate manufacturing begins with water handling and sweetener preparation. Water is filtered to remove suspended solids because solids can seed haze and clog dosing valves. The main sweetener can be sugar syrup, glucose syrup, or a blend. For sugar-based concentrates, granulated sugar is dissolved in heated tanks with agitation until the solution becomes clear. Density is monitored because it defines sweetness and freezing behavior after dilution. For syrup-based sweeteners, the syrup is held warm so viscosity is stable, and metering is accurate. Acidity is set next because pH affects flavor perception and stability. Acid is prepared as a liquid solution for accurate dosing and then injected into the blending tank. pH is measured and adjusted to a narrow set point. A stable pH also helps preserve certain flavor components. Color is handled as a separate dosing stream. It is stored in tanks with gentle mixing and filtered before dosing so it remains uniform. Flavor is prepared as a concentrate that can be dispersed reliably in water. Many slush flavors contain both water-soluble aroma components and oil-based notes. Oil-based components are emulsified, so they do not separate in the finished concentrate. Emulsification is done with high shear mixers that reduce droplet size. Droplet size matters because large droplets separate and ring at the surface, while small droplets remain stable and deliver consistent aroma. The finished flavor concentrate is filtered to remove particulate and then metered into the main blending tank. Viscosity modifiers can be included in small amounts to influence mouthfeel and crystal suspension. These components must be fully hydrated and dispersed, so they are added under controlled shear and allowed to mix until uniform. The goal is not a thick beverage, but a mix that can hold microcrystals evenly during dispensing and drinking. Once sweetener, acid, color, flavor, and any stabilizers are in the blending tank, the concentrate is mixed to uniformity without entraining air. Air entrainment can cause foaming in packaging and can affect how the concentrate mixes with water later. The concentrate is then filtered to remove any remaining undissolved particles that could settle or clog dispensing systems at retail. Quality checks on the concentrate focus on soluble solids, pH, color density, and flavor strength. Soluble solids are measured to ensure the dilution ratio will yield the intended freezing point depression. pH is checked for consistency because it affects taste and stability. Color is checked because it must remain stable in storage and consistent from batch to batch. The concentrate then moves to packaging. Packaging is designed for high sugar liquids. Concentrate is filled into jugs, bottles, or bag-in-box systems. Bag-in-box is common because it minimizes oxygen exposure and allows easy dispensing at retail. Filling uses metered valves and is controlled to avoid splashing and foaming. Caps or fitments are applied immediately. Seals are checked because leaks allow contamination and sugar crystallization around closures. Finished packages are coated and cased. At retail, the concentrate is mixed with water to the specified ratio. That mixing can be done in a separate tank or directly in the machine reservoir. The purpose is to produce a ready mix with the correct sugar concentration and acidity. The water used at retail can vary. So many systems specify filtration and cold water use to reduce variability. Inside the slush machine, freezing is achieved by a refrigerated cylinder and a rotating scraper. The cylinder wall is cooled below the freezing point of the mix. A thin layer of ice forms on the cold wall. The scraper continuously removes that ice layer and breaks it into small crystals that are pushed into the bulk liquid. Continuous scraping prevents the ice from building into a solid sheet that would block heat transfer. The rotating mechanism also keeps the entire mixture moving so ice crystals remain suspended rather than settling. The formation of microcrystals is controlled by the freezing point depression of the mix. Sugar and dissolved solids lower the freezing point so the mixture does not freeze solid at typical machine temperatures. Instead, a fraction of the water freezes as ice, while the remaining liquid becomes more concentrated. This concentrated liquid phase acts as a lubricating syrup between ice crystals. The machine aims for a steady balance where ice fraction stays in a target range. Agitation speed is a key control. If agitation is too slow, ice crystals grow larger and the product becomes coarse and icy. If agitation is too fast, the mixture can incorporate air and become foamy, and frictional heat can reduce freezing efficiency. The scraper geometry and clearance are engineered to remove ice efficiently without creating excessive shear that would heat the mixture. The machine also relies on viscosity to prevent separation. If the liquid phase is too thin, ice crystals can settle and form a dense, icy bottom layer, while the top becomes watery. A slightly more viscous liquid phase helps keep crystals evenly distributed. This is why concentrates often include small amounts of stabilizer and why the soluble solids level is strictly maintained. Temperature control in the machine is staged through a thermostat system that cycles refrigeration. The goal is not a constant deep freeze, but a controlled temperature near the mix's freezing curve. If the machine overcools, ice fraction rises too high, and the product becomes stiff and difficult to dispense. If it undercools, ice fraction drops, and the product becomes slushy syrup. Machines often use sensors that monitor torque on the agitator as an indirect measure of slush stiffness, adjusting cooling accordingly. From a factory perspective, this machine behavior drives the formulation targets. The concentrate must produce a ready mix with a predictable freezing curve. That means controlling sugar type and concentration. Different sugars and syrups depress freezing point differently and change viscosity. The factory chooses a sweetener system that creates the desired crystal fraction at typical machine temperatures. Acidity and flavor intensity are also tuned with the machine in mind. Cold temperatures reduce flavor perception. Therefore, the ready mix is formulated with enough flavor concentration to remain noticeable when frozen. Acidity can provide brightness that cuts through cold dullness. However, acidity also affects the stability of certain emulsions and can influence syrup behavior over time. The factory balances these factors. Color stability is another practical requirement. Slush is displayed in clear machine bowls and must remain visually uniform. Colorants must remain stable under light exposure and cold temperatures. The factory filters concentrate to remove particles that would settle and create gradient bands. Coca-Cola starts with treated water. Incoming water passes through filters that remove suspended particles. It may move through activated carbon beds, ion exchange systems, and fine membrane filters. These stages produce water with a consistent mineral profile, taste, and clarity. The treated water enters stainless steel storage tanks. The tanks are sealed and fitted with sensors that monitor level, temperature, flow, and pressure. From there, pumps send the water toward the syrup room. In the syrup room, granulated sugar or liquid sweetener is measured into a mixing tank. Warm treated water is added to help dissolve it. Large agitators turn inside the tank, pulling the sweetener downward and folding it back through the liquid. The surface changes from cloudy and grainy to smooth and clear. The syrup is filtered again to remove any undissolved particles. It then moves into another stainless steel vessel, where Coca-Cola concentrate is added. The concentrate contains the flavoring system and caramel color. It is dosed in carefully controlled amounts. Flow meters and load cells measure the addition with high precision. The concentrate enters as a dark stream and spreads through the syrup as the agitator spins. The mixture becomes a finished syrup. It is dense, glossy, and intensely flavored. It is not yet the final drink. It still needs to be diluted with treated water and carbonated. Before blending, the syrup may pass through a deaeration step. Removing excess oxygen helps protect the flavor and improves carbonation performance. A vacuum chamber pulls dissolved gases out of the liquid. Tiny bubbles rise and collapse as the pressure drops. The finished syrup is pumped to a proportioning unit. This machine combines syrup and treated water at a fixed ratio. The two streams enter through separate pipes and meet inside a blending chamber. Sensors check flow rate continuously. Automatic valves make small corrections so the mixture stays uniform. The blended Coca-Cola then moves toward the carbonation system. Carbon dioxide is fed from pressurized storage. The gas is filtered and regulated before it reaches the carbonator. The beverage is chilled because cold liquid absorbs carbon dioxide more efficiently. Heat exchangers lower the temperature quickly as the liquid flows through thin channels or tubes. Inside the carbonator, the chilled beverage meets carbon dioxide under pressure. The gas dissolves into the liquid, forming the sharp, sparkling texture of the finished drink. The system keeps the beverage enclosed so the carbonation stays locked in. The carbonated Coca-Cola is now ready for filling. On a plastic bottle line, PET preforms may be made or supplied separately. These preforms look like small, thick test tubes with finished neck threads. They are heated in an oven with infrared lamps until the plastic softens. The preforms then enter a blow molding machine. Each hot preform is clamped inside a bottle mold. A stretch rod pushes downward, extending the plastic. Compressed air bursts into the preform, forcing it outward against the mold walls. In less than a second, the small tube becomes a full-size bottle. The mold opens and the bottle emerges warm, clear, and rigid. For glass bottles, formed bottles arrive already molded. They pass through inspection systems that check shape, cracks, chips, and contamination. Light beams and cameras examine the mouth, base, sidewall, and interior. Any defective bottle is pushed off the line automatically. Cans follow a different path. Aluminum cans arrive open at the top and move through air rinses. They are inverted, blasted clean, and returned upright before filling. The filling machine is the fastest and most precise stage. Bottles or cans enter a rotating filler with dozens or even hundreds of filling valves. Each container lifts toward a valve. The valve seals against the opening. Pressure inside the container is balanced with the pressure in the filler bowl. This prevents foam from erupting when the carbonated drink enters. The liquid flows down the container wall in a controlled stream. Filling is measured by level, volume, or mass, depending on the system. The container reaches the exact fill height, the valve closes, and the container moves away. The sound is continuous and rhythmic. Clinking glass, humming motors, clicking star wheels, and short bursts of gas pressure. Immediately after filling, the container is sealed. Plastic bottles pass under a capper. Caps are sorted in a bowl feeder, lined up in a chute, and delivered one by one to the capping heads. Each head picks up a cap, places it on the bottleneck, and twists it to a specified torque. The tamper band locks beneath the neck ring. Glass bottles may receive crown caps. A capping head presses the metal crown over the lip of the bottle. The ridged edge folds tightly under the glass bead, creating a gas-tight seal. Cans go to a seamer. A lid is placed on top of each filled can. The can spins, while seaming rolls curl the lid edge and can flange together. The metal folds into a tight double seam that holds carbonation under pressure. After sealing, the containers pass through inspection. Fill level sensors check whether each bottle or can contains the correct amount. Cap inspection cameras verify position, angle, and seal presence. Pressure or vacuum detectors check closure integrity. Label sensors, code readers, and vision systems examine alignment and printed marks. Any container outside tolerance is rejected by a fast pneumatic arm or air jet. It leaves the mainstream without slowing the rest of the line. The sealed Coca-Cola then moves toward labeling. Plastic bottles may pass through a roll-fed labeler. A thin printed film unwinds from a roll and is cut into individual labels. A small strip of adhesive is applied to the leading and trailing edges. The label wraps around the bottle as it rotates against a drum. Other bottles receive pressure-sensitive labels. These peel from a backing web and press onto the container surface with foam rollers. The rollers smooth the label so it follows the bottle's curve without wrinkles. Glass bottles may receive paper labels with cold glue. The labeler picks up each label, coats it with adhesive, and presses it onto the glass. Brushes wipe the label flat as the bottle spins. For cans, decoration is usually printed directly onto the aluminum before filling. After sealing, cans still receive a date code and batch code. Coding machines apply production information to each container. Inkjet printers spray tiny droplets onto the cap, shoulder, base, or can bottom. Laser coders may etch the mark into the surface. The code is brief, sharp, and traceable. The containers then pass through drying tunnels or air knives. High-speed air strips away condensation and rinse water. This gives the surface enough dryness for packaging equipment to handle it cleanly. Next comes grouping. Bottles travel into lanes formed by guide rails. Timing screws separate them into exact spacing. The machine gathers them into packs of 6, 12, or another format. Colliders push the bottles into rectangular patterns. For shrink-wrapped packs, a sheet of plastic film wraps around the group. The pack enters a heat tunnel. Hot air shrinks the film tightly around the bottles. The plastic grips the shoulders and bases, forming a compact bundle. For cardboard cartons, flat blanks feed from a magazine. The machine opens or folds the board around the bottles or cans. Glue nozzles apply hot melt adhesive. Compression belts press the flaps until the glue sets. Cans may be packed into trays. A corrugated sheet folds upward around the base of the group. The tray holds the can steady while film wraps over it or while the open tray moves directly to palletizing. The finished packs travel along conveyors to the palletizer. Cases are turned, aligned, and arranged into layers. A robotic arm or gantry system lifts each layer and places it onto a pallet. Sheets of cardboard may be inserted between layers to stabilize the stack. The pattern changes from one layer to the next so the load locks together. Pepsi production begins with the concentrate stream, not the bottle. The strongest part of the drink is prepared first as a dense syrup base. This is where Pepsi's process is closest to Coca-Cola's process, but not identical in sequence or formulation control. Both products rely on treated water, sweetener, caramel color, acidity regulators, flavor concentrate, carbonation, high-speed filling, sealing, coating, and packaging. The difference is in the exact concentrate composition, the syrup ratio, the flavor profile, and the control settings used by each bottling system. In the syrup room, stainless steel tanks receive measured quantities of treated water. This water is not yet the final beverage water. It is used as the carrier for dissolving sweetener and dispersing the concentrate. The tank is fitted with a high-torque agitator. Its blades rotate below the surface, pulling liquid downward and creating a controlled vortex. Dry sugar, high fructose corn syrup, or another approved sweetener stream is metered into the tank depending on the plant and region. The sweetener dissolves under continuous agitation. At first, the liquid looks thick and uneven. Fine crystals or dense syrup ribbons move through the water in slow folds. As mixing continues, the liquid becomes smooth, heavy, and uniform. Temperature control helps the sweetener dissolve fully without damaging the flavor components added later. This syrup making stage is similar to Coca-Cola's syrup preparation, but the ingredient balance is Pepsi specific. Coca-Cola syrup is built around Coca-Cola concentrate and its own acid and flavor system. Pepsi syrup receives Pepsi concentrate, which produces a slightly different balance of sweetness, citrus-like brightness, spice notes, caramel tone, and acidity. The machines may look almost identical, but the dosing recipe and quality targets are different. The sweetened base is then filtered. The syrup passes through fine filters that catch undissolved particles or any small solids from the mixing stage. The filtration unit protects the downstream proportioner and filling valves from clogging. A clear syrup stream leaves the filter and flows into a finished syrup tank. Pepsi concentrate is added with precise metering pumps. The concentrate is dark, aromatic, and highly concentrated. It enters the sweetened base through a closed line, usually beneath the liquid surface to reduce splashing and air pickup. Load cells beneath the tank or magnetic flow meters in the pipe verify the amount being added. The agitator keeps the tank moving so the concentrate spreads through the syrup evenly. Caramel color gives the syrup its deep brown-black appearance. The liquid darkens quickly as the color disperses. Under the tank light, the syrup appears glossy and almost opaque. Every turn of the agitator folds the darker stream into the lighter sweetener solution until the entire batch reaches a consistent shade. Acid ingredients are blended into the syrup system to create the sharp taste structure of the finished cola. In Pepsi, this balance is adjusted to match Pepsi's formula, while Coca-Cola uses a different acid and flavor balance for its own profile. The production equipment does not need to understand the taste difference. It follows programmed weights, flow rates, and mixing times. Before the syrup can be turned into a finished drink, the water used for final dilution must be prepared separately. Incoming plant water enters a treatment system. It may move through sediment filters, activated carbon beds, softening or ion exchange units, polishing filters, and ultraviolet or membrane treatment stages. The goal is consistent water with controlled taste, mineral content, clarity, and microbiological quality. This water preparation step is almost the same in Pepsi and Coca-Cola bottling. Both brands depend on water consistency because the final beverage is mostly water. Any mineral shift can change the way sweetness, acidity, and carbonation feel. The treatment system removes variation before the drink is built. The treated water is stored in sealed stainless steel tanks. Level sensors track the volume. Temperature sensors monitor the water condition. Pumps move the water through sanitary pipework toward the blending and carbonation area. The pipework is smooth, closed, and designed to avoid dead zones where liquid could remain trapped. The finished syrup and treated water now meet in a proportioning system. This is a key point of comparison with Coca-Cola. Both products use proportioners to combine syrup and water at a fixed ratio. The difference is the exact ratio and formula specification. Pepsi's system is calibrated for Pepsi syrup. Coca-Cola's system is calibrated for Coca-Cola syrup. The same type of equipment can produce both kinds of soft drink, but the recipe program changes the final result. Inside the proportioner, syrup flows through 1 meter and treated water flows through another. Control valves adjust constantly. The machine does not simply dump ingredients together, it measures each stream in real time and keeps them locked to the target ratio. If the water flow changes, the syrup flow corrects. If syrup pressure shifts, the valve compensates. The blended liquid is still flat at this point. It has Pepsi's flavor, color, sweetness, and acidity, but it has no sparkling bite. Before carbonation, the liquid is often chilled. Cold liquid absorbs carbon dioxide more efficiently than warm liquid. The beverage passes through a heat exchanger where chilled glycol or another cooling medium runs on the opposite side of thin metal plates or tubes. The Pepsi stream loses heat rapidly as it moves through the exchanger. The next stage is deaeration and carbonation. Excess oxygen can interfere with flavor stability and carbonation quality, so the beverage water or blended liquid may pass through a deaerator. Under vacuum, dissolved air is pulled out. Tiny bubbles rise from the liquid and collapse inside the chamber. The liquid becomes quieter and more ready to absorb carbon dioxide. Carbon dioxide enters from pressurized storage through regulators and filtration. The gas is delivered at controlled pressure. In the carbonator, chilled Pepsi meets carbon dioxide under pressure. The gas dissolves into the liquid instead of forming large bubbles immediately. The system is sealed, so the carbonation stays in solution. This stage is nearly identical in principle to Coca-Cola's carbonation stage. Both drinks rely on cold liquid, pressure, and controlled carbon dioxide flow, but the carbonation target can differ depending on package type, market, and product specification. A can, a PET bottle, and a glass bottle may each require slightly different pressure behavior during filling. While the beverage is being prepared, the packaging line is already moving. For PET bottles, production may begin with small preforms. Each preform has a finished neck, threads, and tamper band support ring, but the body is short and thick. The preforms feed into a heating oven. Infrared lamps warm the plastic, while the preforms rotate so the heat spreads evenly around the circumference. A transfer wheel carries the softened preforms into the blow molder. Each preform drops into a bottle mold shaped like the final Pepsi bottle. A stretch rod plunges downward, pulling the plastic lengthwise. Then compressed air bursts inside. The hot plastic expands outward until it touches every detail of the mold wall. Panel shapes, grip contours, base petals, and shoulder curves appear in a fraction of a second. This is the same mechanical principle used for Coca-Cola PET bottles, but the mold design is brand and package specific. Pepsi bottles may have different shoulder geometry, label panel proportions, base design, or volume shape. The process is similar, but the final plastic form is different because the mold cavity is different. The new bottles leave the mold and move directly toward rinsing or air cleaning. They are lightweight, clear, and warm from forming. Neck handling conveyors grip them below the threads. Air jets or mechanical guides keep them aligned as they travel. Glass bottles follow another route. They arrive already formed and inspected. The line checks the mouth finish, sidewall, base, and internal cleanliness. Cameras and light sensors examine the glass. A defective bottle is rejected before it can reach the filler. Aluminum cans also begin as empty containers. They arrive open at the top. The cans move through a twist rinser or air rinser. Each can is inverted, blasted with filtered air or rinsing fluid, drained and returned upright. The metal makes a light rattling sound as the cans move in tight rows along the guide rails. The filling zone is where the prepared Pepsi and the empty package finally meet. In a rotary filler, containers enter through a star wheel. The wheel spaces them perfectly and delivers each one beneath a filling valve. The container rises or the valve lowers. A seal forms around the opening. For carbonated Pepsi, the filling system must control pressure carefully. If the pressure changes too quickly, foam forms and the fill becomes inaccurate. The filler first equalizes pressure between the container and the filler bowl. Carbon dioxide may be used to pressurize the empty container. Then the beverage flows in. The liquid enters smoothly, often directed along the inner wall to reduce turbulence. Foam stays low. The fill height rises until the sensor or mechanical fill tube reaches the target level. Compared with Coca-Cola filling, the machinery again performs the same basic task, but it is tuned to Pepsi's carbonation level, package, temperature, and syrup characteristics. Even small differences in foam behavior matter. A cola that foams slightly faster may need a different valve timing, sniff setting, or filling speed. Fanta production begins with orange syrup, forming inside a closed stainless steel tank. Treated water enters first. It has already passed through filtration, activated carbon, and polishing stages to remove particles, odors, and unwanted mineral variation. This gives the drink a neutral base before any flavor is added. A measured amount of this water flows into the syrup tank. The agitator starts slowly, then builds a steady rotation. The blades pull the liquid downward and push it outward against the tank wall, creating a smooth, rolling motion. Sweetener is added into the moving water. In some plants, it is granulated sugar. In others, it is liquid sugar or another approved sweetener system. If dry sugar is used, the crystals fall into the vortex and begin dissolving. The liquid turns slightly cloudy at first, then becomes clearer and heavier as the sweetener fully blends in. Warmth may be applied through the tank jacket or an inline heating system. The heat helps the sweetener dissolve faster and keeps the syrup consistent. The mixture thickens, reflecting light in slow waves as the agitator turns. The sweet syrup is filtered before flavoring. It passes through fine filters that catch undissolved particles. This protects the later equipment, especially flow meters, proportioning valves, and filling heads. The filtered syrup moves into a second blending tank. This is where Fanta begins to separate from cola production. Cola syrup is dark, spicy, and caramel heavy. Fanta syrup is brighter, fruitier, and usually built around citrus flavor, acidity, color, and sometimes a clouding system. Orange flavor concentrate is dosed into the sweet syrup through closed lines. Metering pumps control the amount precisely. A small volume of concentrate flavors a much larger volume of syrup, so the dosing must stay exact. The concentrate enters below the surface of the liquid. It disappears into the moving syrup and spreads through the tank. The agitator keeps the mixture uniform, preventing strong pockets of flavor from forming. Color is added as part of the concentrate system or as a separate ingredient, depending on the formula. The syrup shifts from pale yellow to a dense orange tone. It looks much stronger than the final drink because it has not yet been diluted. Acid is blended next. Orange soda needs a sharp citrus edge to balance its sweetness. Citric acid is commonly used because it creates a bright, fruit-like bite. The acid dissolves into the syrup until the flavor base reaches the required balance. Some Fanta formulas include emulsified citrus oils. Citrus oils do not naturally mix with water, so they must be dispersed into tiny droplets and held in suspension. Stabilizers keep the droplets evenly distributed. This gives the drink a fuller, slightly cloudy appearance instead of a perfectly clear look. The mixing speed matters at this stage. Too little movement leaves uneven flavor. Too much shear can damage the emulsion structure. The tank keeps the syrup moving with controlled force, enough to blend, but not enough to break the system. The finished syrup is dense, sweet, acidic, aromatic, and strongly colored. It is not yet drinkable. It is a concentrated base that must be diluted with treated water. The syrup flows toward the proportioning unit. A separate stream of treated water arrives from storage tanks. Both streams pass through flow meters. The proportioner continuously compares the syrup flow with the water flow. The machine adjusts valves in real time. If the water flow rises, the syrup feed changes with it. If syrup pressure drops, the system corrects the ratio. The goal is a constant blend from the first bottle to the last. Inside the blending chamber, the thick orange syrup meets the treated water. The color brightens. The texture becomes lighter. The flavor spreads through the full liquid volume. At this point, the drink looks close to finished Fanta, but it is still flat. Before carbonation, the liquid is chilled. The beverage passes through a heat exchanger made of thin metal plates or tubes. Cold glycol or another cooling medium runs on the opposite side. Heat moves out of the drink quickly while the liquid remains sealed inside the system. Cold liquid absorbs carbon dioxide better than warm liquid. This step also helps reduce foam during filling. If the beverage were too warm, it would release gas too quickly and fill unevenly. The chilled liquid may pass through a deaeration stage. A vacuum chamber pulls dissolved air out of the beverage. Tiny bubbles rise and collapse as the pressure drops. Removing excess oxygen helps the flavor stay stable and prepares the drink for carbonation. Carbon dioxide arrives from pressurized storage. Regulators reduce and control the gas pressure. The gas passes through filters before entering the carbonator. Inside the carbonator, the chilled Fanta meets carbon dioxide under pressure. The gas dissolves into the liquid. It does not simply bubble through and escape. Pressure, temperature, and flow are balanced, so the carbonation stays locked inside the drink. While the liquid is being prepared, the containers move through their own production path. For plastic bottles, PET preforms are fed into a heating oven. Each preform looks like a thick test tube with finished neck threads. Infrared lamps soften the plastic while the preforms rotate so the heat spreads evenly. A transfer wheel carries each hot preform into a mold. The mold closes around it. A stretch rod pushes down through the center. pulling the plastic lengthwise. Then, compressed air blasts inside the preform. The softened plastic expands against the mold wall. The bottle shape appears almost instantly, including the base, shoulders, grip panels, and label area. The mold opens and the new bottle moves out, still warm and clear. If glass bottles are used, they arrive already formed. They pass through inspection before filling. Cameras and light beams check the mouth, sidewall, base, and interior. Cracked, chipped, dirty, or misshaped bottles are rejected automatically. If cans are used, empty aluminum cans arrive open at the top. They pass through an air rinser. Each can is inverted, blasted with filtered air, and turned upright again before filling. The filler brings the finished drink and the container together. Fanta is carbonated, so the filling machine must control pressure carefully. Containers enter through a star wheel and move beneath filling valves. Each container seals against a valve. Pressure is equalized before liquid enters. The orange drink flows into the container in a controlled stream. It is guided to reduce turbulence and foam. The liquid rises smoothly from the bottom until it reaches the correct level. The valve closes immediately after the target fill is reached. The container leaves the filler and moves straight to sealing. Plastic bottles pass under a capper. Caps are sorted, lined up, and delivered to rotating capping heads. Each head places a cap on the bottle and tightens it to a set torque. The tamper band locks below the neck ring. Glass bottles receive crown caps. A metal crown is pressed over the mouth and crimped under the glass bead. Cans move to a seamer, where a lid is placed on top and folded into a tight double seam, then extended open boiling. Final moisture content is the main structural setting. Too much moisture yields candy that stays tacky and softens quickly. Too little moisture yields candy that becomes overly brittle and cracks at the stick interface during cooling or later handling. Immediately after concentration, the mass enters a controlled cooling section. The aim is to bring the mass to a forming temperature that is still fluid enough to be deposited and shaped, but not so hot that it degrades flavor and not so cool that it begins to set in pipes. Heat exchangers and jacketed manifolds manage this temperature precisely. At this stage, additives are introduced because many flavors contain volatile compounds that would be stripped or damaged at peak cooking temperatures. Color is prepared as concentrated solutions or dispersions and filtered so no particles clog injectors or create specks. Flavor is metered by precision pumps into the candy stream. Injection is placed after the main heat load so aromatics are preserved. Acid can be introduced as a solution if the recipe calls for a sharper profile. But acid timing is controlled because acid accelerates sucrose inversion at high temperature, which changes viscosity and long-term stickiness. Mixing after injection is done with static mixers or low-shear mixing manifolds that fold the flow and eliminate streaks without entraining air. Air entrapment is undesirable because bubbles create weak zones and can appear as surface pits once the candy cools. The candy mass then feeds the depositor at the forming wheel. The depositor meters a precise amount into each cavity. Portion volume directly sets lollipop size and weight. Metering is done by piston pumps or gear pumps synchronized to the wheel index. Dose accuracy matters because a low fill yields thin spots and poor stick anchoring, while an overfill creates flash that must be trimmed and increases wrapper puncture risk. The cavity receives the candy dose first or simultaneously with stick insertion depending on machine design. In one approach, the cavity is partially filled, then the stick is inserted, then a second small dose tops off and the cavity closes. In another approach, the cavity closes on a measured candy slug and the stick is driven into it. The common requirement is that candy must be plastic at the moment the stick enters, so the candy wets the stick surface and bonds as it cools. Shaping occurs when the cavity closes. The closing motion forces candy into the spherical geometry and expels trapped air. Venting channels can allow small air pockets to escape so they do not remain as bubbles. Cavity surface finish is polished, so the candy skin releases cleanly. Cavity temperature is managed, so candy does not stick or smear. If cavities are too cold, the candy skin sets instantly and can trap air. If cavities are too warm, the candy remains tacky and can deform during demolding. The machine therefore maintains a stable mold temperature through internal circulation. As the formed lollipop exits the cavity, it is still hot enough that the interior is not fully glassy. It immediately enters a cooling system that locks structure. Cooling is staged. The first stage sets the outer surface quickly so the shape stops flowing. This can be done with cool, dry air directed at the candy surfaces. The second stage brings the core temperature down so the entire mass crosses into the glass state. Cooling rate must be controlled because excessive thermal gradients create stress. Stress tends to concentrate around the stick insertion zone because the stick acts as a rigid inclusion and the candy contracts around it. If the outer layer contracts much faster than the inner, microcracks can form. These cracks may be invisible initially, but can propagate during shipping or when humidity changes. Humidity control in cooling is essential. Hard candy absorbs moisture from air. If cooling air is humid, a thin moisture film can form on the warm candy surface. This film dissolves sugar at the surface and then recrystallizes as a rough haze, reducing gloss and increasing stickiness. Cooling tunnels therefore use dry air. Some lines control dew point directly, keeping dew point low enough that condensation cannot form on the candy at any point in the tunnel. Once cooled to handling temperature, lollipops are demolded or released from the forming wheel and transferred to conveyors. Transfer points are designed to avoid impact at the candy head because the surface can still mark if it is too warm. Guides support sticks rather than candy heads because contacting the head can create flat spots. The lollipops pass through inspection and rejection systems. Vision systems can detect off-center sticks, incomplete fill, surface bubbles, and flash around seams. Weight checks can detect underfill and overfill. Reject mechanisms remove defective pieces before wrapping because wrapping a defective piece wastes film and creates downstream jams. Twizzlers are manufactured by converting a cooked sweet base into a plastic, elastic candy dough, shaping that dough continuously through extrusion, setting texture through staged drying and cooling, then cutting and wrapping so the ropes stay chewy and separate without sticking. The most useful place to start is the cutter, because the cutter reveals whether the upstream dough has the right cohesion and whether the rope has been set enough to hold its geometry. If the rope tears at the cut, the dough is underhydrated or too cold. If it smears and strings, the dough is too warm or too wet. The factory therefore tunes the entire process to deliver an extrudate that behaves predictably at the knife. Upstream of the cutter, the rope travels through setting tunnels that control moisture and temperature. Those tunnels are what convert an extruded ribbon into a stable Twizzler's rope with a uniform chew. The rope exits the die warm and pliable, and its interior still contains enough water to make it sticky if packaged immediately. The setting tunnel removes a measured amount of moisture while allowing the matrix to equilibrate so the surface becomes dry enough to handle, yet the core remains chewy. Air temperature, humidity, and velocity are balanced to avoid case hardening. Case hardening creates a tough outer shell and a soft interior, which leads to cracking during bending and an uneven bite. Staged zones, warmer early zones, and gentler later zones reduce that risk. Before the rope ever reaches those tunnels, the line creates the candy dough in a cooker and mixer system designed for high solids. Sugar and glucose syrup are staged as the main carbohydrate system. Granulated sugar is screened to remove clumps and dust because clumps dissolve unevenly and dust can scorch at hot surfaces. Glucose syrup is held in jacketed tanks so viscosity stays stable for metering. Water is filtered and tempered because inlet temperature shifts dissolution and cook stability. Starch and other structure-building solids are held dry and fed accurately because their hydration rate determines dough firmness later. Cooking starts in a dissolver where sugar is hydrated into a clear solution. That solution then moves to a cooker where heat drives off water and raises solids. The cook endpoint is selected so the base becomes plastic when cooled, not glassy like hard candy and not fluid like